Good evening. Can you hear me? Good evening, everyone. So yesterday we have seen CMRR, and today we will solve one or two problems on CMRR. So find CMRR. CMRR of the difference amplifier given. Calculate CMRR. So yesterday we have seen a simple formula for CMRR. What is the simple formula? A1 minus A2 by 2 times of A1 plus A2. A1 minus A2 by 2 times of A1 plus A2, that is CMRR. So find CMRR of the difference amplifier. So CMRR is given as A1 minus A2 by 2 times of A1 plus A2. And let us calculate A1 and A2 separately. A1 equal to V V2 is 0. So let us take the same difference amplifier and replace V2 with short circuit. V2 is grounded here. So I'll call this intermediate point as VP. VP. Am I right? So what is V0 by V1? V0 by V1 can be written as V0 by VP into VP by V1. So what is V0 by VP? This is a non-inverting amplifier. The gain is 1 plus RF by R1. And what is VP by V1 by voltage division? It is 10K by 1K plus 10K. So 10 into 10, 100, 100 by 11. So this is going to be your A1. This is A1. A1 is V0 by V1. I have split that into V0 by V1 can be written as V naught by Vp. The intermediate point is Vp into Vp by V1. Suppose if 10K is not there, if this 10K is not there, then op-amp draws no current. Then Vp and V1 both are same. Vp and V1 both are same, is it not? Unless and until the examiner mentions, right? If he says op-amp does not draw any current, right? The op-amp gain is high, you can always apply virtual ground, right? So that is what I told you. We have to alleviate the problem one by one, right? In this circuit, we are only concerned about CMRR, how well our amplifier can associate itself with the different signals and how it can kick off or eliminate or reject the corruption, which is the common mode noise. So that we are going to calculate, right? In fact, CMRR is actually the differential gain by the common mode gain. So a simple way of calculating AD and ACM is with A1 and A2. Okay. Now what is A2? What is A2? A2 is V naught by V2 when V1 is 0. So V1, you can ground it. Only V2. This is 1K and the resistor is 9K. Of course, this is an inverting amplifier. What is the gain of inverting amplifier? Minus R2 by R1 times of V2. Am I right? It is minus 9K minus R2 by R1. Minus 9K by 1K. Minus 9. Minus 9. A1 is 100 by 11. A2 is minus 9. What is CMRR? A1 minus A2 by 2 times of A1 plus A2. 2 times of A1 plus A2. So what is 100 by 11? How much is 100 by 11? It is 100 by 11 minus of minus 9 by 2 into 100 by 11 minus of 9. So 11 nines are is 99. 100 plus 99 is 199, right? So 100 minus 99. 199 by 2. So what is 199 by 2? So it is 99.5 is CMRR. What is CMRR in dB? It is 20 log 99.5. So tell me, what is 20 log 99.5? Very good. 39.95 dB. Very good. 39, because 100 is 40 dB. So 99.5 should be less than 100. 39.95 dB. Very good. So this is CMRR. So CMRR is nothing but A1 minus A2 by 2 times of A1 plus A2. A1 minus A2 by 2 times of A1 plus A2. So I told you 60 dB and above is always a good choice, is it not? Okay, this is a gate problem. So much of mismatch is there. Instead of 10K, you have 9K here. What if this 9, instead of 9K, it is 10K? If it is 10K, then the calculation would have been infinite because your ACM is 0. Your ACM is 0 if you have 10K here and 10K also here. Instead of 9K, you just as a homework, instead of 9K, you replace it by 10K. and calculate. When you calculate, CMRR will be infinite. But a practical circuit, there will be mismatch in the resistors, and every resistor is bound to have some tolerance, So naturally, a practical difference amplifier like this with 1K here, 1K here, 10K here, and 10K here is going to give you a finite CMRR. It is not going to be infinite CMRR, right? Because resistors have tolerance. And especially in IC, I told you, resistors are diffused resistors, so they have wide tolerance. But there are so many technologies where you do laser trimming and all that, and you improve the accuracy of resistors, right, on an IC. But even if you spend a pile of gold also, you cannot get exactly two resistors which are same, right? So definitely there will be some mismatch. So CMRR can never be infinite. You will always have a finite CMRR. But in this gate problem, this is completely imbalanced, is it not? 1K, 10K, it should be 1K, 10K, but examiner is giving 9K. No problem. And the CMRR you have seen, it is worst, is it not? It is not that good, only 40 dB, right? Less than 40. Let us see one more gate problem. Let's see what the examiner has planned for this, right? Let's calculate CMRR. So as usual, A1 minus A2 by 2 times of A1 plus A2. Let's calculate A1 first. It is V0 by V1 when V2 is 0. It is V0 by V1 when V2 is 0. V0 by V1 when V2 is 0. So we have grounded it. So naturally, if this is 0, this node is also at 0 volts. So you can have entering current equal to leaving current. So tell me KCL. What is KCL? 0 minus, and here this is V1. So this node is also at V1. All right, 0 minus V1 by R equal to V1 minus V0 by 10R. V1 minus V0 by 10R. So what is V0? V0 by V1 is going to be 1 plus RF by R1. 1 plus 10R by R, that is going to be 11. So this is A1. A1 is going to be, is something like the non-inverting, is it not? Input is given to the non-inverting terminal, and instead of ground, that is at virtual ground. So 1 plus 10R by R, it is 11. Similarly, what is A2? V0 by V2 when V1 is 0. V0 by V2 when V1 is 0. So let us ground the V1 terminal now. So now tell me, if this is ground, this voltage is also 0. All right. This is V2. Entering current equal to leaving. So let's apply KCL. V2 minus 0 by R equal to 0 minus V0 by 10R. So what is V0 by V2? This is like the inverting amplifier, minus RF by R1, minus 10. It is minus 10. A2 is minus 10 and A1 is 11. So what is CMRR? A1 minus A2 by 2 times of A1 plus A2. So it is 11 minus of minus 10 by 2 times of 11 minus 10. So it is 21 by 2. 21 by 2. This is also was 10.5. So what is CMRR in dB for this gate problem? It is 20 log 10.5. It is 20 log 10.5. So what is that? It's slightly more than, if it is 10, you'll have 20 dB, right? So it should be slightly more. So how much is this? $20.42, right? 20.423. Good. So CMRR for this is 20.42. Very good. Okay, now what is the disadvantage in the first difference amplifier? Why the first difference amplifier cannot be used for instrumentation applications? Cannot be used for an instrumentation application. What is basically a good difference amplifier? A good difference amplifier should have all the good qualities of a good voltage amplifier, because you are taking V1 as voltage, V2 are also in voltage form. So naturally it should be a good voltage amplifier. So what is the characteristics of a good voltage amplifier? A good voltage amplifier should have high input resistance and low output resistance. Then it can take the signal perfectly in voltage form, right? To take a signal in voltage form, it should have high input resistance and low output resistance. But if I use this amplifier as a difference amplifier, then what is the disadvantage? The disadvantage is, so yeah, we are going to solve this. So what is the, if you take this amplifier, what is the disadvantage in this difference amplifier? If you calculate CMRR for this, I told you, I want you to take this as a homework and calculate CMRR. You'll find that CMRR for this is going to be infinite. Why CMRR is infinite? Because ACM is 0. ACM is 0. What is ACM? ACM is A1 plus A2. Now you might say, how did I know ACM is 0? Because A1 is exactly minus A2. So for this amplifier, if you calculate A1 and A2, you will realize that A1 is exactly minus A2, because for V1, this is going to be R2 by R1 plus R2 into 1 plus R2 by R1, which is R2 by R1. But for V2, it is going to be minus R2 by R1. So finally, what is your V naught? The differential gain is going to be R2 by R1 times of V1 minus V2. So A1 is R2 by R1 and A2 is going to be minus R2 by R1. So naturally, CMRR when you calculate, it is going to be infinite. Okay, fine. So this is like the A1 V1 plus A2 V2. But still, this is not the instrumentation amplifier. This is not the instrumentation amplifier. We cannot use it as an instrumentation amplifier. What is the disadvantage in such a circuit? The disadvantage is a good voltage amplifier or an instrumentation amplifier which is taking a signal in voltage form should have high input resistance and low output resistance. Now, if you calculate the input resistance here, Rin, what is the input resistance seen through non-inverting terminal alone? The input resistance Rin, if you apply a voltage source, these two are in series. So Rn is going to be R1 plus R2, which is through the non-inverting. If you see the input resistance through the inverting, here, input resistance. What is input resistance? V by I. You apply a voltage V and find I. This is virtual ground. Here R1. So V by I, Rin through the inverting terminal is going to be R1. Here, if you apply a voltage through non-inverting terminal, it is going to be R1 plus R2. So that means it is not, none of the input resistance through non-inverting and inverting is infinite. It is infinite, right? And moreover, what is the differential input resistance? Suppose the same problem is given. If I say calculate the differential input resistance RID and the common mode input resistance RCM. So for this amplifier, what is this differential input resistance? Input resistance through non-inverting is R1 plus R2. Input resistance through inverting is only R1. Then if you calculate the differential input resistance means if you connect a signal between the two terminals. So if you have two lines, I told you 4 input resistances you can calculate. If there are 2 lines, 4 input resistance. What are the 4 input resistance? One is through this terminal. One is through this terminal. So here we are connecting a voltage from here to ground. The second input resistance is you will connect a voltage between the two terminals. That is called the RID, differential input resistance. It all depends on where you connect the voltage. So if there are 2 lines, 4 ways you can connect the voltage. One is only through this line. One is only through this line. One is between. One is you can short and connect a voltage. If you short and connect a voltage, then it is called the common mode input resistance. So let's calculate the differential input resistance. So RID, if you want to calculate, then you have to connect the voltage between the two terminals. Between. And we know that virtual ground, so the potential difference is 0. So what happens if I connect a voltage V here and I? This is R1 and R1. Small chota KVL you can apply, right? So the KVL says that minus to plus, minus V plus I into R1 minus 0 plus I into R1 equal to 0. So V by I is going to be 2R1. This resistance is called the differential input resistance. Of course, this is a gate problem. The differential input resistance between the two terminals is also not infinite. So this is not at all a good VCVS. A good instrumentation amplifier should be a good VCVS. Input resistance through plus is R1 plus R2. Input resistance through minus is R1. Input resistance between the two terminals is going to be 2R1. And what is the common mode input resistance? A common mode input resistance is, we have to short both the terminals now and calculate. You have to give a common signal. So if I short here, this voltage becomes the common signal. So this is the input resistance seen by noise, because noise is a common signal. So we are applying some test voltage here. This is a test voltage to calculate the input resistance due to noise. R1, R2, R2. And this voltage is 0. Am I right? Now, what is the potential difference here? This is V minus 0. This is also V minus 0. So naturally, this current will divide into half. Right? So whenever 2 resistors are same and the voltage is also same, naturally the current should be same. Isn't that? So the voltage here is V minus 0, V minus 0. So I by 2, I by 2. This I by 2 will flow here. This I by 2 will flow here and it will sink through the ground, right? It will go to the op amp. Now, what if I take a KVL in this loop here? Can you see here? it is minus V plus I by 2 into R1 plus I by 2 into R2 equal to 0. So what is V by I? It is R1 plus R2 by 2. This is going to be the common mode input resistance of this amplifier. So if you calculate, nothing is infinite here. So this is a worst difference amplifier, but what we have to do, what are the disadvantages? To solve the input resistance problem, we connect a VCVS at each of the balance line. Right? So this circuit is the instrumentation amplifier. So if you see now, if you look at the third circuit, see this is a beautiful circuit. Now, what is the input resistance seen here? Rin. Current is 0. If current is 0, infinite. What is the input resistance seen here? Current is 0. Because non-inverting terminal will not draw current, infinite. If you short and apply a voltage, infinite. If you connect, infinite. Excuse me. So the input resistance problem is completely eliminated by connecting two VCVS here, right? But if you take only this difference amplifier here, naturally your CMRR will be high. So for this circuit, I want you to calculate V1, V2, every node voltage, VA, VB, Vx, Vy. Every node voltage. Okay, so let's calculate all the node voltages in this instrumentation amplifier. So what is V1? First, V1 is V1 by 2 plus V2 by 2 plus V1 by 2 minus V2 by 2. So this is going to be VCM plus VD by 2. So VCM is given, VD is given. So it is going to be 5 plus 1.5 sine omega t millivolt, because VD is 3 sine omega t. Similarly, what is V2? V2 by 2 plus V1 by 2 plus V2 by 2 minus V1 by 2. So V1 plus V2 by 2 is VCM minus VD by 2. It is going to be 5 minus 1.5 sine omega t millivolt. So this is V2. Now, according to virtual ground, V1 and VA both are same. V2 and VB are also same. And this is equal to V. Because this node and this node are same because of virtual short. So V1 is known, V2 is known, VA is known, VB is known, right? Then what is Vx, Vy and V0? Vx, Vy and V0. Of course, this R1, R2 we know. If this is R1 and this is R2, R1 and R2, then V0 is R2 by R1 times of Vx minus Vy, right? But with VA, VB, how can we calculate Vx, Vy? Suppose if I assume some current I here is the same current I, because op-amp draws zero current. Op-amp draws zero current. So let us have KCL. The current I is Vx minus Va, Vx minus Va by 50K equal to Va minus Vb by 1K. So Vx minus Va by 50K equal to Va minus Vb. This is Va and Vb. What happens if you subtract Va minus Vb? Va minus Vb, the DC 5 volts is getting cancelled. 1.5 minus 1.5, that is going to be 3 sine omega t millivolt by 1K. So then what is Vx? It is going to be, Va is 5 plus this. So it is 5 plus 150 plus 1.5. 151.5 sine omega t millivolt. Your Vx is going to be 5 plus 151.5 sine omega t millivolt. So you can have one more KCL here. What about Vy? If this current is I, then this current will also be I, all right? So tell me, what is Vy then? One more KCL, I, Va minus Vb, Va minus Vb by 1K equal to Vb minus Vy by 50K. From here, your Vy is going to be 5 minus 151.5 sine omega t millivolt. So you know Vx and you know Vy. So what is V0? V0 is going to be R2 by R1 times of Vx minus Vy. It is 10K by 1K times of Vx minus Vy. Tell me what is Vx minus Vy. If you subtract 151.5 plus 151.5, that is going to be 303, right? 303 sine omega t millivolt. So that into 10 is millivolt. 3.03 sine omega t volts you are going to get, V naught. See, such a beautiful amplifier, this one. See here, I am giving you a noise signal or a common signal of 5 volt. 5 volt DC is there. See, instrumentation engineers will love this. The reason is, whenever a transducer is connected, a microphone or whatever, there will be a large DC over which a small perturbation will be there, a small signal. Now this amplifier should amplify only this amplifier should not amplify this 5 volt. Over this 5, there will be a small perturbation. This is your voice signal. It is actually the 5 being disturbed. You know, when you talk over a microphone, over that 5 volt, the signal is getting disturbed like this, right? That's the signal. Now, this 5 volt DC has to be rejected. Only the signal has to be amplified. Now, how is this possible that the DC, which is the common signal, is rejected? So what they do is, when you connect a transducer here between the 2 points, it will have a common DC here, common DC here. So when V1 is 5 volt, V2 is 5 volt, VA will be 5 volt, VB will be 5 volt, then what is I? What is I if your VA is 5 and VB is 5? Your I is 0, no current will flow. When there is a common signal applied, V1 is 5 volt, V2 is 5 volt, VA is 5 volt, VB is 5 volt, current is 0. That means same 5 volt will come, it will come to the next section. The same VA will be 5, current is 0, no drop. Same VA and VX are 5. So 5 volt has come, and what is V naught? V naught is R2 by R1 times of 5 minus 5. So your VA will be 5, your VY will also be 5. Nicely, that 5 minus 5 gets rejected. But the moment V1 and V2, if you apply a signal between the 2 terminals, then your V1 is going to be half of the signal, V2 is going to be the other half with 180 degrees phase shift. So here at the V1 node, there is VD by 2, and V2 node, there is minus VD by 2. The difference is VD. So what happens if I apply VD here? If I apply VD, this difference is VD. That means one end goes up, the other end comes down, right? So one end goes up, the other end comes down. Nicely, your VA and VB are going to, what is VA minus VB? Tell me. If you apply VD between the 2 terminals, can you see that there is a virtual short? There is a virtual short. Complete plus terminal of this complete plus terminal will appear here. Complete minus terminal is going to appear here. Then this whole voltage is going to be VD. If you apply VD here, complete VD is going to appear here. That means VA, mathematical representation, what we are saying, VA is VD by 2, VB is minus VD by 2. That means what? The difference is VD only. So now happily current will flow. Small millivolt signal will be there. Nicely current will keep on flowing. And this 3 sine omega t millivolt has now become 3 volt amplification. But the DC is rejected. The DC is rejected. This is 0 right here, or we draw it like this. So finally, you have a DC of 5 volt over which there is a 3 sine omega t millivolt. And finally, what happened? You got a 3 sine omega t, and the DC or common signal is rejected. So this amplifier will amplify only the signal. So can you imagine a millivolt signal is being amplified, but a 5 volt DC is being rejected, right? So because when you give DC, your VA will be DC, your VB will be DC, and the current is going to be 0, there's no amplification, right? So you can see even in this equation, see, that is why if I directly tell you the output, you may not enjoy it. You have to see step by step. V1 had DC, V2 had DC. Your Vx had DC, but without amplification. But the signal has been amplified from 1.5 to 151.5. The signal has got amplified, but you're nicely the 5 volt passed to the next stage. And the last stage, the 5 volt is kicked. The 5 minus 5 is going to become 0. And the 151.5 minus of minus 151.5 has become 300, and then 303, and then amplified by 10 times. Are you getting? So why 2 stages? Because this stage gives you only a gain of 10. This one, right? The second gain stage. This is a gain 2 stage. It gives a gain 10. There's a gain 1 stage. The gain 1 stage is very intelligent. Apart from decreasing the burden on gain 2 stage, this gain 1 stage is rejecting the common signals, right? It's nicely passing the same common signals to the next stage, and it is amplifying only the different signals. And what is the input resistance of this? The input resistance to non-inverting and inverting is very large. So this classic amplifier is called what amplifier? Instrumentation amplifier. So this is a nice mathematical representation. Instead of just saying the whole VD appears here, the whole VD appears here. When I give VD, I'm getting VD. So the mathematical representation says that VA has VD by 2 and VB has minus VD by 2, and the difference is going to be VD. So complete signal is going to get applied there. But if you give 5 volt, what happens if you give DC here, 5 volt and 5 volt? Then this will be 5 and this will be 5, and the current is going to become 0, right? Okay. Is my voice audible? Is my voice audible? Yeah. So what happens if noise is a common signal? When a common DC of 5 volt is rejected, naturally a common noise will also get rejected, is it not? Any variation that is similar, if your VA goes up by 1 millivolt and your VB also goes up by 1 millivolt, then the current is going to become 0, right? The current is going to become 0 for all the common variation. But for the signal that you're applying, definitely the signal that we are applying between the two terminals is a differential signal. It is going to get applied completely across that 1K. That is why this 1K you can use for calibration. The 1K, suppose an instrumentation engineer, he wants to, yeah, of course, V0 is voltage. So if you put a voltmeter here, voltmeter, And this voltmeter should measure anything, should measure say temperature. If you want to make a thermometer, right? So the temperature variations, this should be 50K, this should be 50K, this should be 1K, 1K, 10K, 10K, right? Everything should be balanced. But this 1K here, you can use it for calibration. That means when you adjust this 1K potentiometer, you can have full scale reading. Suppose on this, you can have some readings here. Suppose you want to make it as 0 to 100 degrees of what you call meter, which can measure 0 to 100 degrees centigrade. So whenever you give 100 here, you want full scale reading. You want full scale reading. And suppose your meter rotates only till here, half. You want to make full scale reading, so you can increase the gain. So that 1K is used for calibration, right? So you can use it for calibration, but please don't disturb 50K and 10K like that, right? So 50K, it should be perfectly balanced, 50, 50, 1, 1, 10, 10. But the middle one, you can use for calibration for adjusting the gain. And of course, this 3 op-amp instrumentation amplifier is also available in IC form. It's also available in IC form. Okay. And one more non-ideality or the limitation of op-amp is the gain bandwidth product. The gain bandwidth product is also called unity gain frequency. In radians per second, it is denoted by omega t. In hertz, it is denoted by ft. The gain bandwidth product is nothing but the unity gain frequency. So an ideal op-amp should have infinite bandwidth. An ideal op-amp should have infinite bandwidth, but a practical op-amp has finite bandwidth, is it not? In fact, you'll be surprised to know that the bandwidth of op-amp is very small, almost 10 radians per second. Open loop bandwidth, high gain will be there, but bandwidth is going to be very, very small. Now, what is the reason that the bandwidth of op-amp is very, very small? The reason is, suppose if I have an op-amp, and just imagine op-amp has only one capacitor in it. Op-amp has only one capacitor inside. Of course, you cannot design, even a single transistor will have 2 capacitors. But generally, if you open any textbook, you open any control systems textbook, they will first explain what happens in a first order system, second order, and then more than second order, that is the third order or more, the behavior is going to be same. So if you have one capacitor or first order, what happens when I apply a signal? I apply a signal Vin, or you apply some noise. Noise means what? Some disturbance. Just switch on the power supply. The circuit is subjected to noise, because when you switch on the power supply suddenly, you are giving a step input. The frequency domain analysis of step input, if you see the spectrum of step, you'll get a sinc function. That means just giving noise is nothing. Just switch on the supply, that is enough. Circuit will have noise in it. So if circuit does not have noise, it is a big news. Every circuit is subjected to noise. The moment you switch on the supply, finished, you are giving a step input. Its frequency domain analysis, if you see sinc function, all sine waves will be there, right? You just switch on the supply, transient state, every sine wave you are giving. But if you give feedback, what happens? All the sine waves will go round and round and round and round and round. Are you getting? But when they go from source to destination, they will have gain. And then they come back here, right? So what happens if there is only one capacitor? If there is only one capacitor and you give all sine waves ranging from low frequency to high frequency, high frequency. Low frequency, we have seen a first order system which is of the form k by 1 plus s tau form, k by 1 plus s tau. From low frequency will have 0 degree phase shift. Slowly, you're going to have 10 degree, 20 degree, and by the time you give a high frequency, there will be 90 degree phase shift. There will be 90 degrees phase shift. So all the sine waves which go from source to destination will not experience more than 90. But when you give negative feedback, you are already giving 180 degrees phase shift in negative feedback. What is 180 degrees phase shift here? When you subtract two signals, what happens when you subtract two signals? Subtraction means addition of the inverted signal is called subtraction. What is subtraction? What is 3 minus 2? 3 minus 2 means 3 plus of minus 2. 3 minus 2 means 3 plus of minus 2. So 180 degrees phase shift is already given in negative feedback. If the system gives an additional 90 plus 180, 270, it will not oscillate. Any signal to oscillate, it should experience what is Barkhausen criteria. I mean, the next topic when you take up oscillators, you'll realize that if the loop gain is greater than 1 and at some frequency, it's not exactly, we don't know what frequency is this. At some frequency, if your loop gain is greater than 1 and angle A beta, the forward path, if it experiences 180 degrees, then the system is unstable. The system is unstable. Why it is 180? Because negative feedback will give an additional 180. Negative feedback is going to give you an additional 180, 360 degrees phase shift. And what happens if the gain is greater than 1? Nicely the signal will come, one loop, one period, one loop, one period, one loop, one period. With more gain, it is going to burst into oscillations. So, if you want a system to be unstable, in the forward path, 180 degrees phase shift should not be there. First order system is excellent, stable. Any sine wave you give, maximum 90. Negative feedback will give additional 180. 180 plus 90 is 270. It will not oscillate. Second order system is also okay because if this is having second order, then from a low frequency to high frequency, the forward path will give you 0 to 180, but 0, 10, 20, 90, 110, 150, 170, some sine waves will give. But at 180, there won't be any gain because if you draw a low pass filter like this, at the highest frequency of operation, gain is not there. So no problem. Even if you are giving from, this is omega axis. No? So high frequency, the phase shift will be there, but gain will not be there. But what happens in a third order system? Now, what happens in a third order system? In a third order system, you're barely out of luck, finished. Some frequency will be there, some chore frequency will be there, some donga frequency will be there, where the forward path delay is exactly half its period. So what happens when the system is third order or more? Third order or more, what will happen? Definitely at some frequency, highest frequency is 270. Between 0 to 270, some sine wave will be there, 180 degrees. At this frequency, the circuit will oscillate. The circuit is going, if you have a third order system, pakka it is going. See, simple, I'll tell you, every circuit will oscillate here. Forget it. It is not that, sir, third order will oscillate. No. You give it negative feedback means it will oscillate. In fact, if you ask me, who is more stable, open loop systems or closed loop systems? I would say closed loop systems are hopeless systems. Every closed loop negative feedback system is hopeless. Every system is going to oscillate. But if you don't do frequency compensation, then it is a useless system. You open any control system book, they say open loop systems are stable, closed loop systems are unstable. Why they are unstable? Even if you have 3 capacitors, you give negative feedback, it is going to oscillate. You have to throw it. Can you design an adder circuit from this useless op-amp? The moment you connect an amplifier, what will happen? Suppose you want to add 2 numbers, 1 volt, 2 volt. What is 1 volt plus 2 volt? 3 volt. Instead of 3 volt, if sine wave comes, what you will do? You will pull your hair. 2 volt plus 1 volt is what? 3 volt. No 3 volt is there. Some 50.3 kilohertz sine wave will come. What you will do? You will think, why this sine wave has come? Whether you give 1 volt, 2 volt or 5 volt, 6 volt, sine wave will come. Every circuit will oscillate. You cannot sell this. You cannot sell this op-amp. Are you getting? Because third order system or more, if you give negative feedback, it will pick some signal where the delay from the forward path to the destination, source to destination is 180. 180 additionally will negative feedback will give. 180 plus 180 is 360, finished. Circuit will oscillate. For a circuit to oscillate, the loop angle should be 360 degrees. If the loop gain is greater than 1, finished. Nicely it will come. One loop with more gain, second loop with more gain, third loop with more gain, finished. It is going to oscillate. So if you ask me who will oscillate, every circuit in this world will oscillate if you give feedback. That means are feedback circuits good? They are very bad. All feedback circuits are bad. They are highly unstable. You have to throw them. Then if you ask me, sir, then how negative feedback has all these advantages, this, that, then how are we going to achieve that? Yes, you have to do something called frequency compensation. If you don't do frequency compensation, nobody will buy your op-amp. Why they will not buy? Because they cannot design any circuit. Before they connect an input, sine wave will come. That fellow will pull his hair from where this sine wave has come. So that is why we need what? Frequency compensation. What is frequency compensation? Op-amp is a multiple pole system. With many transistors and junction capacitors. Op-amp is a multiple pole system with many transistors and junction capacitors. If such an op-amp is given negative feedback, what happens? If such an op-amp is given negative feedback, the output is fed back to input and subtracted. Subtraction means 180 degrees phase shift. Subtraction means if such an op-amp is given negative feedback, the output is fed back to input and subtracted. Subtraction means what? 180 degrees phase shift. If at any particular frequency, the delay offered by forward path is additional 180. That means total angle is what? Forward path 180, feedback 180. 180 plus 180 is 360. Then the circuit will oscillate at this frequency. Therefore, negative feedback system is unstable. Unstable. So if a system is unstable, how will you make it stable? That is the question. If a system is unstable, how will you make it stable? Because the op-amp gain is like this. Here first pole, second pole, first capacitor, second capacitor, third capacitor, fourth capacitor. 25 capacitors are there in an op-amp, right? Or 25 transistors are there in op-amp. So many poles are there. Third order system itself is hopeless waste. Op-amp is a multiple pole system with 25 transistors. Then what will happen to the magnitude? This is the magnitude plot. What will happen to the phase plot? The phase plot will be like this, something like this. At a particular frequency, if this frequency, suppose 55.3 kilohertz, at this frequency, there is an exact 180 degrees phase shift by the forward path. So what will happen if the forward path gives 180 degrees phase shift? The feedback is giving additional 180. 180 plus 180 becomes 360. System you have to throw. Then if you say, sir, what about negative feedback? They are all hopeless waste systems. Negative feedback, you cannot use it. Nobody was ready to buy op-amp here. Nobody was, because initially when op-amp was, they have sold, the business was very less. Why? Because you have to do external compensation. External means what? You have to connect one capacitor here additionally, and that capacitor you have to keep on increasing. You increase. After some time, oscillation will go. Once oscillation goes, again you have to increase little. You have to increase, because you have to maintain something called phase margin. If you don't maintain phase margin, you have to keep on increasing. Oscillation will go. Then you have to do adder circuit. Suppose 5 people have bought, right? 5 people have bought 5 op-amps. First fellow connected capacitor, keep on increasing. Oscillations got, he has used. The same fellow, if suppose another fellow for subtractor, another fellow for what? Each person for his own circuit, they will keep on connecting capacitor and keep on increasing until you avoid oscillations. Who will be ready to buy op-amp? Because people will think, array, old transistor versions are there, no, we will use. This op-amp is hopeless, because once you give feedback, it will oscillate. Then you have to do connect one capacitor and keep on. See, now there are no, because the cell phone era has come, people are playing video games over cell phone. In those days, electronics is mainly for hobby. There are so many people who will do hobby projects. If you go to Amirpet, you will find some old people in Hyderabad. They have no knowledge of electronics, but if you give them a circuit, nicely they will give you it on a breadboard, and those circuits students will take, for projects, for submitting projects and all. If you ask them, they have no knowledge. They will do it on hobby. For a hobby person, can you explain with a person who has no knowledge of electronics, frequency compensation you have to do, connect one capacitor, keep on increasing, he will throw, he'll say, array, old transistor versions are there, I will use, I will not connect capacitor and keep on increasing. Nobody were ready to buy op-amp. Then Fairchild people, as a 23-year-old engineer from Fairchild, that fellow thought, why not do internal compensation? We will connect a large capacitor inside an op-amp that will dominate the frequency response, and it should give so much delay that the delay offered by all other capacitors should be neglected. So they have put one big capacitor inside that will dominate. Frequency compensation is called dominant pole compensation, and op-amp business increased from $1 million to $10 million. Everybody started buying op-amp, because a novice engineer who has no knowledge of electronics, what he will think, these days op-amps are coming without capacitor. Their capacitor is inbuilt inside. So we don't have to do externally, keep on increasing until it goes, oscillations will go. Then today we don't know that. Why? Because op-amps are coming with compensated. When I studied op-amps, right, long back, when I was young in those days. So there are 2 types of op-amps in the market. One is the op-amps with external compensation, where you have to connect a capacitor and keep on increasing. The other one directly connected, which is easy for a hobby project for an engineer. Anything that is done internally, which you don't have to do. But what is the disadvantage? Bandwidth will be very less bandwidth, because if a circuit works for a buffer, it will work for all circuits. So they will connect a buffer and put a big capacitor inside that will dominate the frequency response. Here, what will happen if you connect a capacitor, a big capacitor inside? So before compensation, tell me what is the delay offered by, total delay offered by all the capacitors, total delay tau. Total delay tau is tau 1 plus tau 2 plus tau 3 plus tau 4 up to say tau 50. If there are 50 capacitors before compensation, 50 capacitors is there, op amp is multiple pole, 50th order waste op amp, it is unstable. Now, after compensation, what they will do? After compensation, the delay tau is going to be tau 1 plus tau 2 up to tau 50 plus tau Miller. One big Miller capacitor they will connect. One big, it is a chota capacitor only, but because of Miller effect, it will resemble very big. Now, this should be Miller only. Now, what happens to all the 50 capacitors now? The total delay offered by the system is the delay offered by the single capacitor. Now, if you say that, sir, the total delay is tau Miller, that means how many capacitors are there? Only one capacitor. Op amp behaves as if there is only one capacitor. It is first order. If it is first order, then op amp is stable. So, if you want to convert a multiple pole into single pole, if you want to convert a multiple pole unstable into single pole, what you have to do? You have to put one big capacitor inside that will dominate the frequency. And if you add all the tau, it should again be the total delay offered by the system is the delay offered by this capacitor only. Then you will say, sir, what about all other poles? They are far away. They don't have, they are not going to control the circuit. See here, what happens if I put an additional capacitor? The plot is going to fall like this. If op amp gain is 10 lakhs, by the time you encounter a frequency 10 radians per second, the gain is going to fall like this. This is after compensation. Now, if you ask me, sir, at this gain, this is 0 dB. 0 dB means gain 1. 10 lakhs means 120 dB. At this 0 dB, it should not cross more than 120. So, if you say, sir, where is my chore frequency? At this frequency, 0 dB, this is 0.1, this is 0.01. So, even at 180 degrees, there is no gain, first of all. If you take, sir, what happens at 180 degrees phase shift, the total angle will become 360 and the sine wave, nothing will come, because at this point, it is 120. There is a margin of safety. 60 degree phase margin we will maintain. See, how do we know whether there is 60 or 50? We don't know. What is your job? Simple. If any circuit oscillates, what is your job? If you draw all this to a person who is doing hobby project, he will leave electronics. He will say, what is all this plot? You bring one capacitor, I'll keep on increasing, oscillation will go, I will work, that's all. So if you keep on increasing, put a big capacitor, this is the plot that you get. And it is not going to oscillate. A plot is telling you, because at this, all the frequencies where the gain is, where the angle is 180, the gain is not there. This is called the dominant pole compensation. This is after compensation. This is before compensation. A detailed explanation you will find in control system textbook. Okay. See, I'm not a controls engineer. So my job is only to tell you put a capacitor. But because students are there, I'm explaining. A detailed explanation you can always see in a control systems book. Okay, so all this you can study in controls. Now, let me repeat what I've said. Op-amp is a multiple pole system with many transistors and junction capacitors. If such an op-amp is given negative feedback, the output is fed to the input and subtracted. If at any particular frequency, the delay offered by forward path is additional 180, then the circuit will oscillate, right? Then how will you stop it? How will you stop it? Frequency compensation is a technique used to solve this problem. To solve this problem. What is this frequency compensation? Very simple. Just connect one capacitor, that's all. Connect a large capacitor which will dominate the frequency response the delay offered by this capacitor is so large that the delay offered by all other capacitors is neglected. So op-amp behaves as if it has only one capacitor. One capacitor means first order system. One capacitor means first order system, and first order system means stable amplifier. So if you want a multiple pole to behave as first order, what we have to do? Put one big, if a system is slow and it is unstable, how will you make it stable? You have to make it dead slow. You have to make it super slow. Already we are suffering with capacitors. Now we have to put an additional capacitor and still make it dead slow. Why? Then only $1 million business will be $10 million. Nobody will buy op-amp otherwise. See, everything is motivated by money. You cannot tell your conscious, is it not? I am creating a low bandwidth amplifier. Now, if people buy, I am giving low bandwidth. No. If you want business, what you have to do? From $1 million to $10 million, you have to internally connect because people want it. People want a low bandwidth amplifier, but they are not ready to connect an extra capacitor and keep on increasing it. So they will additionally put one big capacitor inside, which will dominate the frequency response. The system will become stable now, and happily people will buy. Now, if you say that, sir, this is cheating, is it not? 10 power 6 is the gain, 10 radians per second is the bandwidth. This is the bandwidth. Now, if you ask me, sir, with this open loop op-amp, what can I do? No problem. You bring this home and give negative feedback. When you give negative feedback, the gain will reduce and the bandwidth will improve. Suppose if 10 power 6, this is 10 radians. What happens if this is 100? Then this is going to be 10 power 5. Because 10 power 6 into 10 is going to be 100 into 10 power 5. The gain bandwidth product is constant. The gain bandwidth product is constant. This is with negative feedback. So no problem. After giving negative feedback, gain will reduce and bandwidth will improve. But when a person buys op-amp, if he sees the plot, he will cry because bandwidth is only 10 radians per second, gain is 10 lakhs. But after giving negative feedback, the gain will reduce and the bandwidth is going to improve. The bandwidth will improve because the gain bandwidth product is a constant. So frequency compensation means nothing. Just put one capacitor, the oscillations will go. That's all. Are you getting? Put one big capacitor. But please, when you are doing it on an analog board, suppose an analog board comes to me and I want to do frequency compensation. What we have to do? We'll connect some capacitor, the shunt arm, keep on increasing. Once the oscillation will go, we should not stop, please. You have to still increase. Keep some phase margin. You have to maintain a margin of safety such that if you still increase, then happily, otherwise customer will call. If you slightly increase, tomorrow some noise, some problem will come. Again, if it oscillates, that fellow will again give a call. Then again, you have to shift that plot, isn't that? So it is better that you maintain a margin of safety. That margin of safety is called phase margin. So what is phase margin? What is this plot? What is this dominant pole compensation? You will study in controls, right? But in analog, it's very simple. Connect one capacitor, and this capacitor should give so much delay that the delay offered by all other capacitors is neglected. So now, what is this cutoff frequency here? Omega 3 dB here. This is going to be 1 by tau. It's going to be 1 by tau, or it is 1 by tau Miller, right? But where will you connect this capacitor? Where will you connect this capacitor? I told you, capacitors cannot be fabricated, no? Capacitors cannot be fabricated. So what that 23-year-old engineer did is, he connected a capacitor in the second stage. Second stage. This was, I think, 1 picofarad capacitor. But the gain of this circuit is suppose minus 1000. Then according to Miller effect, that is going to be C multiplied by 1 plus 1000. It is 1001 C. 1001 C will be the effect of that. So if you ask me, sir, where he has connected that capacitor, and that single capacitor made $1 million into $10 million business, that is in the Darlington pair. So I have drawn a Darlington pair, if you remember, right? So here the signal is small, here the signal is large. See, in analog, what they did, by connecting a capacitor here, they made $10 million, $1 million to $10 million business. Because this capacitor, Miller, is going to dominate, is going to make the system stable, right? But externally, if you are doing one capacitor, we will connect, keep on increasing. But capacitors cannot be fabricated on an IC. That is why a chota capacitor should resemble big capacitor, means you have to use what technique? Miller technique. So they put a capacitor between the 2 points. Okay, see why I'm telling all this is, tomorrow somebody asks you in an interview, what is frequency compensation in an op-amp? At least you should be able to tell him that if you connect one large capacitor, an unstable system will become stable. That is the intention, isn't that? So he will feel happy. Sir, one big capacitor we have to connect. The delay offered by that capacitor should be so large that all other parasitic capacitors is neglected. Because even if you add the delay, then this capacitor delay is so large, all are neglected. So op-amp will behave as if there is only one capacitor. One capacitor means first order. First order means stable amplifier. If you want a stable amplifier, then you have to connect a big capacitor, right? Okay. So for all gate problems, the op-amp will have a transfer function like this. See here? The open loop gain A is given as 10 power 6 by 1 plus S by 10. So what is this S by 10? This is in a gate problem, if the examiner gives like this, you have to think that that is a good op-amp. It has only one capacitor in it. It behaves as if there is only one capacitor. All the parasitic capacitors inside are neglected. 10 power 6 by 1 plus S by 10. Find CLTF. What do you mean by CLTF? Closed loop transfer function, CLTF, and the 3 dB bandwidth. 3 dB bandwidth. Find the CLTF and the 3 dB bandwidth. So all this story is why this S has come, why only one S has come in a gate problem. You open some gate problems are given like this. why that S has come, why there is only one capacitor and op amp, right? For that, I have given some explanation. A detailed explanation of this you will study in a subject called control systems. Control systems, you can study what is called the dominant pole compensation, right? In analog, it is just connecting one extra capacitor. So whenever reactive elements are there, what is the problem? Whenever your reactive elements are there, frequency domain analysis is split into two parts: magnitude analysis and phase analysis. The analysis itself tells that whenever you put j omega, as frequency changes, phase will change, magnitude will change. Are you getting? Frequency, whenever it is changing, but in resistor, what will happen if a small voltage divider is there? In a voltage divider, if you change the frequency, only magnitude will change. Suppose 1k is there, Vin is 5 sine omega t, output will be 2.5 sine omega t. Yes or no? Voltage divider. Magnitude only will change. But if a resistor divider has capacitor also in it, a resistor and a capacitor, then magnitude will change, phase also will change, right? Remember, that is what is called frequency response. So till now, we were worried only about magnitude. Now phase, see how much problem phase is creating. If there is 180 degrees phase shift, you are giving with negative feedback. Forward path, if there is any small chore frequency which will give 180, 180 plus 180 becomes 360. Finished. 360 means you have to throw. System will oscillate. Are you getting? So now you give any frequency, it will not oscillate, because at larger frequencies there is no gain. At very large frequency, what is happening at very large frequency in this plot? Phase shift will be there, but the gain will be 0.001. With 0.001 gain, what will happen when the signal goes to a loop? It will 0.001, 0.001, 0.001, 0.001 gain. So gain less than 1 means what? Finally in a loop, it is going to die down. But danger is this. Danger is this part where where the gain is more than 1. So whenever the gain is more than 1, there should not be even a single frequency which will give 180 degrees phase shift, right? For that, what we have to do, just put one capacitor, that's all. The problem is going to get solved, right? Okay. So this is A. What is beta? Beta. So this, I have an amplifier A. I have an amplifier A. And I have a resistor divider here. Resistor divider. I am applying V. So this is R2 and this is R1. R2 is 3K, R1 is 1K. This section I am calling it beta, this section I am calling it A. So what is the gain in negative feedback? V0 by Vin, which is the gain with feedback, is nothing but A by 1 plus A beta. It is A by 1 plus A beta. Am I right? So what is beta? Beta is going to be this factor, Vf by V0, Vf by V0, feedback factor, which is R1 by R2 plus R1. So beta is going to be 1K by 3K plus 1K. It is 1 by 4. 1 by 4. So now you have to substitute. So to substitute A 2 times is a big headache. I'll divide numerator and denominator by A beta. So it is 1 by beta by 1 plus 1 by A beta. So let me write it here. The gain V0 by Vn is going to be 1 by beta by 1 plus 1 by A beta. A is the gate problem. A is 10 power 6 by 1 plus S by 10. Beta is 1 by 4. 1 by 4. So substitute. If you substitute 1 by beta is 4 by 1 plus 1 plus s by 10 by 10 power 6 into 1 by beta is 4. It is going to be 4 by 1 plus 4 by 10 power 6 plus 4s by 10 power 7. So this is neglected. It is going to be V naught by Vn is going to be 4 by 1 plus s by 10 power 7 by 4. So next time you should not do all this nonsense, right? We are going to make a very, very powerful conclusion here. What is that powerful conclusion here? Next time, don't do all this. Just observe what will happen in a closed loop transfer function. Closed loop. Open loop transfer function, can you see what is OLTF here? Open loop transfer function. 10 power 6 by 1 plus s by 10, op-amp. After that, closed loop transfer function is 4 by 1 plus s by 10. So, the numerator is called DC gain. It is called DC gain by 1 plus s by 3 dB bandwidth. 3 dB bandwidth. 3 dB bandwidth. So what is the gain in the numerator? What is the bandwidth in the denominator here? Here in the numerator, before feedback, you had an amplifier with gain 10 lakhs, 10 power 6. It will fall down to 10 radians per second. 10 power 6 by root 2. This is before feedback. After feedback, what happened to the closed loop transfer function? The closed loop transfer function says that the gain has fallen down to 4 and the bandwidth has increased to 10 power 7 by 4. So what is the conclusion here? The conclusion before feedback and after feedback in OLTF and CLTF. This is before feedback. This is after feedback. Before feedback, what is the gain? What is the gain? If I have an amplifier A, which is A naught by 1 plus S by omega 3 dB. What do you mean by this? It is A naught by 1 plus J omega by omega 3 dB. Omega by omega. So what happens here? If omega is 0, then the gain is A naught. So this is called DC gain. It is called what gain? DC gain. DC gain. So what happens when omega is omega 3 dB? When omega is omega 3 dB, it is going to be A naught by root 2. So at omega equal to omega 3 dB, you are going to get A naught by root 2, right? So DC gain is going to be 10 power 6, 3 dB bandwidth is going to be 10. What is the gain bandwidth product? Gain multiplied by bandwidth is 10 power 6 into 10 is 10 power 7. After negative feedback, what happened? What is the new gain? New gain. It is 4. 4. What is the new bandwidth? It is 10 power 7 by 4. What is the gain bandwidth product? 4 into 10 power 7 by 4. It is 10 power 7. So the gain bandwidth product is a constant. Gain multiplied by bandwidth is a constant. Is a constant. The gain multiplied by bandwidth is a constant. Now tell me, when is gain multiplied by bandwidth is bandwidth? When is gain into bandwidth equal to bandwidth? Only when gain is 1. Gain is 1, right? So if you want to consider gain into bandwidth as a frequency, then what sort of frequency will you say? This is also called the unity gain frequency. So what is unity gain frequency? Unity gain frequency is gain multiplied by bandwidth. This is a gain bandwidth product. Let me draw it here. So if you have a, see here, 10 power 6. This is 10. This is 10 power 6 by root 2. Now what happens when the gain falls to 1? When the gain falls to 1, this is going to be 10 power 7. 10 power 7. What do you mean by 10 power 7? This 10 power 7 is 10 power 6 into 10. So gain bandwidth, this is called FT or omega t. Unity gain frequency. Unity gain frequency is gain bandwidth product. Unity gain frequency is gain bandwidth product. It is gain bandwidth product. See, this is not exactly like this. Go like this. Like this. Something like this. Unity gain frequency is gain bandwidth product. So I have proved. Next time, please don't do this. Use this formula. What is the formula? Gain into bandwidth of open loop is equal to the gain into bandwidth of closed loop. That's all. A into B, A1, B1 equal to A to B2. Don't use all this. Don't use all this. Just use the formula. Gain multiplied by bandwidth is a constant. That's all. So by seeing, you can tell 10 power 6 into 10. For this, do we have to do all this? Suppose somebody says, what is the unity gain frequency? What you'll say? 10 power 6 into 10. What is 10 power 6 into 10? Can't you do that in your mind? 10 power 7. For that, we don't have to do all this, right? And what is the 3 dB bandwidth? The gain of this amplifier is 4. 1 plus R2 by R1 is 4. What is the bandwidth? 1 plus R2 by R1 is 4. Gain multiplied by bandwidth is 10 power 7. Bandwidth is 10 power 7 by 4. So by seeing this circuit, orally we can tell the bandwidth of the system, right? So we don't have to do all this to prove that 10 power 7 is a constant with feedback and without feedback. We have just derived it because first time we have to tell the student, right? And next time we will say, please don't do this, right? Don't do this. There is an easy way out. So this is a better sketch here. Can you see? 10 power 6 into 10. If the gain falls to 1, it is going to be 10 power 7. That frequency is called unity gain frequency. Unity gain frequency omega t is going to be the gain bandwidth product. So gain into bandwidth is bandwidth only when the gain is 1. So 10 power 6 into 10 is a frequency where the gain falls to 1. Or you can prove like this. What is gain A? It is A naught by 1 plus j omega by omega 3 dB. Am I right? So if A is 1, if A equal to 1, then the omega is going to be omega t. So what we have to do? 1 equal to A naught by 1 plus j omega t by omega 3 dB. I have to write. It is going to be A naught by root of 1 plus omega t by omega 3 dB whole square. Compared with this factor, 1 is very small. So 1 equal to A naught by omega t by omega 3 dB. So omega t equal to A naught into omega 3 dB. So gain into bandwidth, the DC gain into 3 dB bandwidth is going to be the. So what is the conclusion here? A naught into omega 3 dB equal to omega t. That means DC gain multiplied by 3 dB bandwidth is going to be unity gain frequency. DC gain into bandwidth is going to be unity gain frequency. Omega t equal to A naught into omega 3 dB, right? Okay, then how will you solve the same problem in the exam? How will you solve it without doing anything? Let me change the question here. the gain bandwidth product, the unity gain frequency of the op-amp is 1 megahertz. I'm giving in hertz, right? 1 megahertz, FT, omega t or FT. This is FT because it's in hertz. Find the 3 dB bandwidth of the non-inverting amplifier. Non-inverting amplifier. So if such a problem is given, then please don't do by the previous method. Don't do by the previous method. So what is a simple method now? The simple method is like child's play now, right? We will simply say Ft equal to A0 into F3dB, A0 into F3dB, right? So with feedback and without feedback, this value remains same. With feedback, what is the gain? The gain is 1 plus 99k by 1k. This is a gain. This is 1 mega. And this is F3dB. So what is your F3dB answer? It is 10 power 6 by 100. It is going to be 10 power 4, 10 kilohertz. So the bandwidth of this amplifier is going to be 10 kilohertz. Please don't forget this formula. What is the formula? Unity gain frequency equal to gain bandwidth product, right? With feedback and without feedback, this value will remain unchanged. This value is going to remain unchanged. Unity gain frequency is nothing but the gain multiplied by bandwidth. Gain multiplied by bandwidth for op-amp and gain multiplied by bandwidth of a closed loop system, both are going to be same. So like this, 2 marks they will give, right? But whole story, first story, what did I do? I said, why this transfer function has come? A student will ask, sir, what is this? Till now you said op-amp gain is infinite. Today you are saying op-amp gain is 10 power 6 by 1 plus S by 10. What is this? For this, to explain this transfer function, one story we have built. We said so many capacitors are there, so many S will be there, S1, S2, S3, so many are there, right? Omega 1, omega 2, omega 3, omega 4, up to omega 25, omega 50 will be there. But still, only one frequency, one single pole op-amp behaves. How is this happened? It happened because we intentionally connected one large capacitor, and that's the reason op-amp has become a single pole in all the gate problems. Any gate problem, frequency domain analysis, it will have only one S, right? Don't get worried. It's a good op-amp. It's a good op-amp. Now you can have all the advantages of negative feedback. You can have, in negative feedback, noise will reduce, distortion will reduce, linearity will improve. Are you getting all the desensitization of forward transfer parameter? The gain will depend only on resistors. So all the good advantages of negative feedback you will get. When you will get, if first that system should be made into a single pole. One pole systems are highly stable. Are you getting? If there are 3 poles, 4 poles, 5 poles, means finished. Are you getting? Single pole you have to convert. A system should be first converted into single pole. See, that is why I keep telling to students, is it not? Your life should not be a function of too many variables, right? Only one job. One job if it is there, one wife, one job, single pole. System will be stable. Are you getting? 4 pole, 5 pole means life will go for the dogs, is it not? So you have to first convert that multiple pole system into single pole. Then you will enjoy all the advantages of negative feedback. Negative feedback is excellent, but it is highly unstable, very, very highly unstable. If the poles are more, right? If the poles, too many capacitors in the system will make the system unstable. You want to make it stable, first you convert that multiple pole into single pole. Then you can explain negative feedback is very good. It has got all the advantages, right? You have to first convert that system into single pole. Okay, now is it not easy to solve gate problems now, right? Because the final conclusion is important. Ft is A naught into F3 dB. Unity gain frequency is given. Gain, we know how to find 1 plus R2 by R1, bandwidth, that's all. This is a 2 marks question. This is a simple 2 marks question. Please don't do by this method. Don't do by all this method. The best method is the gain with feedback and the gain without feedback remains same, right? If Ft is given, then A naught into F3 dB you have to do, right? This is a simple way. The unity gain frequency of an op-amp. The unity gain frequency of an op-amp is 1 megahertz. Is 1 megahertz. Find the gain of this amplifier at F equal to 10 kilohertz, 15 kilohertz, and 50 kilohertz. 10 kilohertz, 15 kilohertz, and 50 kilohertz. Okay, so how do we solve this? First, we need a CLTF. What is CLTF? Closed loop transfer function. But we know that the gain multiplied by bandwidth is remains same. So what is a DC gain? The DC gain is going to be 1 plus R2 by R1. It is 1 plus 99K by 1K. That is going to be 100. What is the 3 dB bandwidth? 3 dB bandwidth. The gain, DC gain into 3 dB bandwidth is going to be unity gain frequency Ft. So it is 100 into F3 dB is going to be 1 mega. 1 mega means 10 power 6. So what is F3 dB? F3 dB is going to be 10K. 10K. So what is CLTF? CLTF says that it is A by 1 plus J omega by omega 3 dB or A naught. It is going to be A by 1 plus. Can I write omega as F? Because 2 pi F, right? Omega is written as 2 pi F. So 2 pi in the numerator, 2 pi in the denominator will get cancelled. 2 pi in the numerator and 2 pi in the denominator. So the CLTF says that it is DC gain. This is DC gain 100 by 1 plus J F by 10K. 10K. So this is the closed loop transfer function. Closed loop transfer function. Or it is 100 by root of 1 plus F by 10K whole square. whole square. Am I right? So let's find for different values of f, what is the gain? This is the gain, right? V naught by V. V naught by V. Now, till today, we thought the gain of this amplifier is 1 plus R2 by R1 100. So that 100, today we came to know in a practical op-amp that is wrong. Why? Because only when f is 0, only when f is 0, your V naught by V in is going to be 100. Only when f is 0. Suppose if you give f equal to 10K, 10K, because op-amp itself is a low-pass filter. Op-amp itself is a low-pass filter. If you give f equal to 10K, 10K by 10K, 1 square is 1. V naught by V in is not going to be 100. It is going to be 100 by root 2. 70.7. What happens if f is 15K? 15K. Then V naught by V in is going to be 100 by root of 1 plus 15K by 10K, 1.5 whole square. So somebody with a calculator can help me. What is this value? Calculators. It is 100 by 1 plus 1.5 square. 1.5 square. What happens when f is 50K? Then the gain V naught by V in is going to be 100 by root of 1 plus 50K by 10K whole square. So 5 square is 25. 25 plus 1. So what is this value first of all? Let me see in the comment section. They say it is 55.47. This is for which answer? At 15K, very good. Karthik, very good. 55.4 at 15K. 55.4. What at 50K? At 50K. Sandeep, Atul, Rekha. At 50K, what happens? Mr. Sahi, 19.61, 19.61, very good. 19.61, 19.61, Ganapati, 19.61, Somesh, 19.61, very good. So at 15K, it is 55.4. So that means the gain 1 plus R2 by R1 is only at omega 0. It's only for DC. That is why it's called DC gain. It's called what gain? DC. This 100 is the DC gain. So what happens after that? As the frequency keeps on increasing, the gain will keep on reducing. As the frequency changes, the gain will change. So it's 100 for omega 0. For 10K, it is at 70.7. And then at 15K, the gain fell down to 55.4. And then at 50K. So that means, please take the bandwidth only till 3 dB. Because examiner asked 15K, I'm giving. Examiner asked what happens at 15K. But I just included 0, 0 also, 0, 10 and 50 just to tell you that a practical op-amp is a first order low pass filter. What is a practical op-amp? It is first order low pass filter, and don't worry, the gain multiplied by bandwidth is always a constant. The gain multiplied by bandwidth is always a constant. So this is a gate question. The gate question. The examiner asked what happens at 15K. At 15K, the gain is going to be 55.4. Gain is going to be 55.4. At frequency 0, the gain is going to be 100. Now, in the comment section, many students have said, sir, do we have to suffer with only this gain bandwidth product, or can we increase the gain bandwidth product? Right? So this in the comment section, they said how to increase this product. That means 10 power 6 for a 741. If somebody says the gain bandwidth product is 1 megahertz, so within that domain, you have to play. If you decrease gain, your bandwidth will improve. If you still decrease gain, bandwidth will improve. But can we increase the gain bandwidth product? They are saying that, can we increase the gain bandwidth product? They are saying, sir, I want a larger gain bandwidth product. What should I do? Because when I buy, the op-amp manufacturer says that the gain bandwidth product will remain unchanged. Is it not? Right? Okay. Then think about it. We'll take a break. When I come back, I'll show you how to increase the gain bandwidth product of a system. And the next topic after that will be oscillators. Oscillators, please. Oscillations are good when they are good if the topic is oscillators, because we want oscillations intentionally. Oscillations are bad when they are bad if the topic is amplifier. If I'm designing an amplifier and it oscillates, I have to stop it and connect a large capacitor and stop it. But in the next topic, I will intentionally connect two RC networks or one LC network and control the frequency of operation, the sinusoidal frequency. I will intentionally make the loop gain equal to 1. I will intentionally see that there is a 360 degrees phase shift. Then that is a topic called oscillators. So oscillators is good in which topic? Oscillators topic. Oscillations is bad when I'm designing an amplifier. I don't want him to oscillate, because when an IC is made, people claim that there are two major problems in the IC manufacturing. Once the IC is released, everybody are worried of two things. One, if there is an internal short circuit, what happens? If there is an internal short circuit, then the moment you connect, smoke will come from IC. The second problem is, once you connect feedback, it should not oscillate. So if it bursts into oscillations, again you have to throw, because nobody will buy. These days, every IC is coming with internal compensation. Nobody is going to buy your IC if it oscillates. Or nobody will buy your IC if there is an internal short. Internal short means finished. The moment you connect, the smoke is coming means it is not Diwali, is it not? So internal short circuit should not be there. Oscillation should not burst. But in next topic, externally, we will connect RC network, and we will control the frequency of operation, F equal to 1 by 2 pi RC. In a Colpitts oscillator, F equal to 1 by 2 pi root LC. So we will intentionally, design an oscillator for a particular frequency. Are you getting? So we'll take a break. When we come back, we will take oscillator topic. Okay. Now, can we increase the gain bandwidth product? Can you hear my voice? Can you hear me? Can we increase the gain bandwidth product? So the answer is yes, right? Yes, by a technique called cascading. Right? Very good. Some of you have commented on this. Can we increase the gain bandwidth product? Yes, by cascading, right? But by cascading, how are we going to increase the gain bandwidth product? Because we know that if you cascade two amplifiers, what will happen to the bandwidth? Suppose I have two amplifiers with gain 100. I have two amplifiers with gain 100. If an amplifier has gain 100, then the bandwidth should be taken at 70.7. 70.7. This is your bandwidth, F3 dB. Now two amplifiers with the gain 100. 70.7, right? This is the bandwidth. Now, after cascading, 100 into 100 is 10,000. 100 into 100 is 10,000. But 70 into 70 is not 7,000. If 100 into 100 is 10,000, 70 into 70 is not 7,000. 70 into 70 is going to be 4,900. 70 into 70 is going to be 4,900. But we should not take at 4,900. We should take at 7,000. So at 7,000, if you see, this is your F3 dB total. This is the F3 dB individual. So F3 dB total is less. So by cascading, the first impression which you get is the bandwidth is getting less, right? So what is the relationship between the F3 dB total and the F3 dB individual is? It is F3 dB individual into root of 2 power 1 by n minus 1, where n is the number of stages. The number of stages. If you want, I can derive this also. But right now, you can remember this formula. After cascading, the bandwidth is going to reduce, but the overall bandwidth is increasing. I want to prove that we can increase the gain bandwidth product by cascading. The reason is, suppose if you want a gain of 10,000, you are taking two amplifiers of gain 100 and cascading. Then what is the bandwidth of the small chota amplifiers? Already the amplifier's bandwidth is very large because the gain is only 100, right? Initial bandwidth itself is large. After cascading, naturally little change will be there, but you have taken two small amplifiers and cascaded. What happens if you bring all the bandwidth in a single stage? So suppose there are two amplifiers. I mean, design A and design B. Design A person, what he did is, he took all the gain in a single stage, 10,000, and he got bandwidth. Design B is, he took two 100 amplifiers. When you take 100, gain is less, bandwidth is already very large, individual bandwidth. That individual bandwidth after cascading, it is going to be less. So please see here, can you see my hand here, right? If you bring it from 10 single stage, your bandwidth will be this much, single stage. If you make it from two stages, your bandwidth is going to be this big, two stages. But after cascading, it will become less. So finally, what is happening to your overall bandwidth? Single stage bandwidth is this. Two stage, if you do right, individually it is going to be this. After cascading, it is going to get less. So finally, we understand that the overall bandwidth will still increase. So let me prove that with a problem. the unity gain frequency of a 741 op amp is 1 megahertz. 1 megahertz. Design an amplifier using such op amps to give a gain of 1000 with a 3 dB bandwidth of 20 kilohertz. 20 kilohertz, right? So what is gain multiplied by bandwidth here? 20k into 1000. What is 20k into 1000? 20 into 1000, it is going to be 20 mega. So I want a gain bandwidth product of 20 mega using an op amp of 1 megahertz. How is this possible? Because a gain bandwidth product is a constant. So I want a gain of 1000, but my 3 dB bandwidth should be 20k. If I do the product, it is 20 times of the op amp bandwidth. So I'm using an op amp and I'm going to increase the bandwidth of such an op amp by a technique called cascading. So let's see how we are going to do. First, we will take single stage. If you do single stage, then I told you the gain bandwidth product remains unchanged. So you are not going to improve the bandwidth, right? So single stage, tell me, gain is 1000. So I will connect 999k, 1k, just for simplicity. If I connect 999k with 1k, and what is your unity gain frequency of op amp? FT is 1 megahertz. Now, what is the bandwidth of such an amplifier? Gain multiplied by bandwidth is going to be FT. What is gain? 1 plus 999k by 1k into bandwidth. It is going to be 1 mega, 10 power 6. Then your bandwidth is going to be 10 power 6 by 100. What is 10 power 6 by 100? 10 power 6 by 100 is 10 power 4. It is 10k. No, this is 1000. No? Is this 1000 or 100? 1000. So 10 power 6 by 1000, it is going to be only 1k. This is still worst, right? 1k, 10 power 3, 1 kilohertz. So the bandwidth is now going to be 1 kilohertz. 1 kilohertz. But I want a bandwidth of how much? 20k. Why did I get 1 kilohertz? Because gain is 1000. 3 dB bandwidth is 1 kilohertz. Gain multiplied by bandwidth is 10 power 6. So it's not possible to increase the bandwidth with a single stage. What happens if we take 2 stages? 2 stages. For 2 stages, after multiplying, you should get 1000. After multiplying, you should get 1000. Now, after multiplying, you will get 1000. That means A square is 1000. That means A is root 1000. So I want root 1000 here into root 1000. What is root 1000 into root 1000? After cascading, you will get 1000. But please tell me, what is root 1000? What is root 1000 in your calculator? What is root 1000 in your calculator? How much is root 1000? $31.63. Very good. 31.63 into 31.63 is root 1000. Okay. Now we will design 2 amplifiers with a gain of 31.63. So I'll put 1K here, 30.63. So what is 1 plus 30.63 by 1K? 31.63. This amplifier, we will give it to another op amp. So what is V0 by Vin? V0 by Vin is going to be 1 plus 30.63 by 1K, V0 by Vx into Vx by V. This is V0 by Vx into Vx by V. So naturally, this is going to be 1000. Now, what is FT for individual stage? FT equal to gain into F3 dB. This is 10 power 6. This is root 1000. It is 31.6 root 1000 into F3 dB. So F3 dB is going to be not 10 power 6 by 1000, 10 power 6 by root 1000. It is 31.63 K. Because 31.63 into 31.63 is going to be root 1000, right? So 31.63 K. This is individual for single stage. Now, what happens after cascading? Can you see? After cascading, the bandwidth is reducing. By what factor? F3 dB total is going to be F3 dB individual into root of 2 power 1 by n minus 1, 1 by 2 minus 1. So it is going to be 31.63 into root of 2 power 1 by 2 minus 1. This is approximately 20 point something K. So you have achieved your bandwidth of 20 kiloradians per second by cascading 2 stages. Suppose if you say, no sir, I want more bandwidth, still more, then you can go for how many stages? 3 stages. Of course, 3 stages is easy to calculate. To get 1000, you will get 10 into 10 into 10. Are you getting 10 into 10 into 10? What is F3 dB of individual? It is FT by gain. It is going to be FT is 10 power 6 by 10. It is going to be 100K. Then what is F3 dB total overall? It is individual into root of 2 power 1 by 3 minus 1. So this is going to be almost close to 50K like that. So the total bandwidth, we can still increase more than 20K. So this is going to be around 50 kilo. Around, I don't know. Please tell me the value. Around some value. This is around, I don't know, approximately. So like that, you can keep on cascading. As you cascade, the overall bandwidth is going to increase or reduce. It is going to increase because when you are cascading, you have already taken a small chota amplifier. No? Suppose somebody is cascading 5 stages. Matlab chota will be there. And finally, their individual bandwidth is itself very large. Their individual bandwidth itself is very large. So after cascading, you are going to, somebody said 50.9. So after cascading, little thoda kam hoga, right? It is going to get less, but the overall bandwidth is now going to be more than what you get in single stage. So single stage is a waste of time because if you take single stage, your bandwidth is only 1K. And of course, this orally we can calculate, is it not? If gain is 1000, unity gain frequency of op amp is 1 mega. That means 10 power 6 by 1000, it's going to be only 1 kilohertz. So this is a waste of time, right? But by cascading, we can increase the overall bandwidth. This is for individual stage. So individual stage, it is 100K. After cascading, reduced to 50K. 2 stage, individual stage itself is how much? 2 stage amplifier. Individual stage is 31.6. After cascading, it went to 20. But single stage is worst. Once you give negative feedback, 1 kilohertz is there. only 1 kilohertz, right? You can make it 20, you can make it 30, like that. So first you have to take individual stage with chota gain, which will have a larger bandwidth, and then you can reduce, right? Okay, so these are the non-idealities where questions can be asked. One is current offset, the other one is the voltage offset, right? And then slew rate, CMRR, and the gain bandwidth product. And I have to tell you that, I mean, just as a tidbit, don't think too much about this. Already after compensation, we made it slow, no? The system already after compensation has been made very slow. And who controls the delay offered by the system? The total delay offered by the system is a delay offered by this single capacitor. So when I'm calculating slew rate, dV naught by dt using a step input, right? This dV naught by dt using what input we have calculated? A step input. You know how much this dV naught by dt will be there? This rate of change is only because of that capacitor. No? So if there is some capacitor voltage Vc and there is a current I here, what is Vc? It is 1 by C integral IDT. Am I right? So what is dVc by dt? It is I by C. It is I by C. So this is the current flowing through that Miller capacitor divided by the capacitance I by C. This is your approximate delay offered by the system, dV naught by dt. So it is actually I by C. So the slew rate, the complete slew rate, who is going to decide? The complete slew rate is decided by this large capacitor. So if suppose in the ISRO paper, once he has asked, how do you calculate the slew rate when the current flowing through that Miller capacitor and the capacitance is given? So the slew rate is going to be I Miller by C Miller, right? It is I Miller divided by C Miller. So that is going to be the slew rate, which you have found using step input. So because who gives the delay? The total delay offered by the system is the delay offered by this fat capacitor. So this fat capacitor controls the total delay or slew rate. Then how will you avoid distortion? I told you, how will you avoid distortion? The slew rate dV naught by dt of all the sinusoidal signals, slew rate of all the sinusoidal signals at output should be less than the slew rate of the op amp, which is the slew rate of the system. That means already our system is slow because of the capacitor. Your signal should be still slow. Then you will not have any distortion, right? The slew rate of all the sinusoidal signals at the output should be less than the slew rate for no distortion. So just keep this in mind, right? Who controls slew rate? The big fat capacitor. That big fat capacitor is going to create so much delay that the delay offered by all other capacitors are neglected, right? So if generally examiner will give slew rate, but if he does not give slew rate, and if he gives you the current and the capacitance of that big fat capacitor, then that ratio is going to give you the speed. Because what is time? Time is R and C. What is speed? Speed is I by C. Time is R and C, right? R into C is time and speed is I by C, right? The rate at which the voltage across the capacitor dV naught by dt changes is I by C. This is for no distortion, right? Just keep in mind, right? So who controls slew rate? Is that big fat capacitor. And see, when I'm talking here, suppose there is a public address system. I'm talking over a microphone. When I'm talking over a microphone, how are you instantly listening? Right? How are you able to see that lip sync instantly? It is because that the time scale of the input signal is much larger than the propagation delay of the circuit. The system delay is always going to be, system should be faster. Signal delay should be more, right? Signal should have what? Signal should be slow. right? Who should be fast? The system should be fast. The time scale of my input signal is much larger than the propagation delay of the circuit. So that is why even in communications, you will study that the system bandwidth should always be much larger than the signal bandwidth, right? That's very important, right? So keep that in mind. Who should be fast? Op-amp should be fast. Your signal that you are applying should have a speed which is less than its capacity. Then op-amp will not give you any distortion. Okay, that's it. Okay, now, so we are left with two topics now. One is the sinusoidal oscillators. The triangular wave and square wave we have seen, sine wave we have to see, and then feedback amplifiers, right? Only two topics, sinusoidal oscillator or harmonic oscillator. Sinusoidal oscillator or harmonic oscillator. General configuration of positive feedback. General configuration of positive feedback. So any controls book will give you this general configuration of positive feedback. So what is the gain with feedback? The gain with feedback is given as A by 1 plus A beta is negative feedback. A by 1 minus A beta. A by 1 minus A beta. This is the gain with feedback. Now, an oscillator should not have any input, is it not? It should not have any input. So once the signal is generated, then you realize that's got stuck in a loop, right? It keeps on, it's a generator. Basically, an oscillator is a generator of sine wave. So when will that happen here? If I already have a generator of sine wave, then the condition for that is going to be if A beta is 1. What happens if A beta is 1? Then the gain AF is going to be A by 1 minus 1. It is A by 0. It is infinite. A by 0 is infinite. So what do you mean by an infinite gain? What do you mean by an infinite gain? I'm having an amplifier with gain infinite. What do you mean by that? AF is A by 0, which is infinite. So what do you mean by infinite? Suppose I am having an amplifier of gain 10 and I got some output, 5 volts. I am having an amplifier of gain 1000 and I got an output of 5 volts. I am having an amplifier of gain 10 power 6 and I got an output of 5 volts. What is the difference in all these amplifiers? larger the gain of the amplifier, lesser will be the input. Lesser will be the input, right? For a particular output, if the gain increases, it means the input is getting smaller and smaller in feedback. What happens if the gain is infinite? If the gain is extremely high, then the input will be extremely sukshma. It will be very, very small. Larger the gain, sukshma will be the signal. So it's still larger and larger and larger. If the gain becomes infinite, then there is no need of input. There is no need of input. So mathematically, what do you mean by gain infinite? Infinite gain means with no input, because gain is output by input, no? Gain is always output by input, and it is infinite. What do you mean by output by input equal to infinite? Infinite gains means with no input, we can expect some output. So infinite gain means with no input, we can expect some output. In fact, in an oscillator, there is no input signal. In fact, in an oscillator, there is no input signal. Oscillator works on noise, or circuit transients. So what do you mean by circuit transients? Just switch on, that's all. If you switch on, the sudden change of the power supply is the input for the oscillator. So you might say, sir, what is this? You just switch on, that change that you gave, that itself is the input, right? So oscillator works on noise or circuit transients, right? Okay. So if I remove the input, how will this diagram look like? So I want to remove the input, right? Then how will the diagram look like? Because I'm saying oscillator is a generator. It does not need any input. So if I remove, it is going to look like this, that's all. This is oscillator, right? This is A, this beta. This is an oscillator. And for this amplifier, you just connect some voltage, just switch on, and you get a sine wave, right? You get a sine wave, right? But is this enough? Is this enough? Is A beta equal to 1 enough to build oscillator, to build oscillations? Or should there be a 360 degrees phase shift in that loop? Do you think A beta equal to 1 is enough to build oscillations, or is there something called the phase shift also, right? What do you mean by that? Is A beta 1? A beta 1, what do you mean by A beta equal to 1? A beta equal to 1 is called the Bar-Cousins criteria. What is A beta 1? Please see here. A beta equal to 1 does not mean only 1. It is 1 at an angle 0 or 360 degrees. 1 at an angle 0 or 360 degrees. So that means the magnitude of loop gain is 1, is unity. And the phase angle of loop gain is 0 or 360 degrees. The A beta equal to 1 means 1 at an angle 0 or 360 degrees. The magnitude of loop gain is 1, and the phase angle of loop gain should be 0 or 360 degrees. Together, this is called the Bar-Cousins criteria. It is called the Bar-Cousins criteria for oscillations. The Bar-Cousins criteria says that A beta should be 1 at an angle 0 or 360 degrees. So how do you get this 0 or 360 degrees and gain 1? how are you going to get 0 or 360 degrees and gain equal to 1? Simple. Suppose if I build an amplifier like this, the amplifier gain is suppose I build an amplifier with gain equal to 3. 3 here. This is V in, this is V0. So I'm having an amplifier whose input output is 3, right? This is 3. Output by input is 3. But if I put the same voltage divider here, this is 1K and this is 2K here. What is my V in by V0? V in by V0 is going to be 1K by 2K plus 1K. It is 1 by 3. What is V0 by V in? V0 by V in is 1 plus R2 by R1. It is going to be 3. So this is going to be 1 by 3. So the upper portion is A, the lower portion is beta. A beta is 1. This circuit also follows Barkhausen criteria, right? This circuit follows the Barkhausen criteria, but no sine wave will come, right? This is not an oscillator. This is not oscillator. Though A beta is 1. A beta is 1. That is why A beta equal to 1 is a necessary criteria. Necessary criteria. Not a sufficient criteria. Barkhausen criteria is always a necessary. It is necessary that every oscillator should have A beta 1. But just because A beta is 1, every circuit will oscillate in this world. That is not, just because A beta is 1, it is not an oscillator. But if you have an oscillator and nicely it is oscillating, then A beta will be 1 in that. Oscillate A beta 1 is a necessary criteria, not a sufficient criteria. Not a sufficient criteria. Then when will it be sufficient? Then how can I make an oscillator to oscillate? Then how can I say that, yes, this is going to oscillate? To oscillate, what is important? To oscillate, we have to simulate a second order function. A second order function. We have to simulate a second order function. What is a second order function? The harmonic action. See here, if you have a single capacitor, then the capacitor will always charge in exponential fashion. But if you have an inductor and a capacitor, so it's almost like a spring and a weight, right? If there is a spring and a weight, then there might be oscillations. Or any vibration, you can take a string and hit like this. If it vibrates, right, there will be oscillations. So for oscillations to produce, you have to simulate a second order. Two people should be there. Only one capacitor, one inductor will not be. One inductor, one capacitor. So inductor should transfer its energy to capacitor, capacitor should transfer its energy to inductor. Then a second order function is going to vibrate. It is going to go up, down, harmonic action. So to oscillate, we have to simulate a second order function. In controls, we will say this is complex conjugate pair of poles, no? Complex conjugate pair of poles. So how is this? How is this? We have to simulate a second order function. This is possible. This is possible with two capacitors or two inductors or one LC, at least one LC. This is possible with at least. So that means we need an S square term. So to get an S square term, omega square, right? S square term, you need at least two capacitors, two inductors, or at least one LC network, right? One LC network. If you have this in beta, right? The beta should have at least 2 RC or 2 RL or 1 LC. 1 LC. Then what will happen? If you connect it to an amplifier, and now if your A beta is 1, then the circuit will burst into a sine wave. If you want the circuit to burst into a sine wave, you should have at least 2 capacitors, 2 inductors, or at least 1 inductor and 1 capacitor, 1 inductor and 1 capacitor. So then you can get this harmonic action. Otherwise, it is not possible, is it not? If you say, sir, with 1 single capacitor, what will happen? If a single capacitor, if you excite it with some DC voltage, what will happen? This capacitor is going to give you an exponential like this. That's all. Sine wave will not come. Only a single capacitor will simulate what function? dy by dx plus py equal to q. So this is a linear form. The response is exponential. Exponential. With an inductor and a capacitor, what happens with an inductor and a capacitor? If there is some voltage in a capacitor, say 5 volt in a capacitor, 5 volt, what the capacitor will do, it will nicely discharge. When it discharges, it will come to 0. Once it comes to 0, all the energy is now in the inductor. In the inductor, the voltage is 0. But now inductor itself is a source. When it is a source, it will now reverse its polarity. This will become minus, this will become plus. The capacitor is going to charge in the opposite now. Now capacitor will say, okay, I'm having now, right? This capacitor has to discharge through the inductor. Now again it will become 0. So if you want an inductor capacitor, if you keep them in close proximity, then it's like an electric field and a magnetic field, or it's like a glass of water and the other is empty. You can keep on doing like this, la 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 la, like that, right? So you can keep on, inductor gives to capacitor, capacitor gives to inductor, and you get a nice, pretty nice sine wave. So mathematics says that such a function is not dy by dx plus py equal to q. It has to have an s square term. It has to have an s square if you do in frequency domain, right? In time domain, it will be like d square y by dx square plus p dy by dx plus ky equal to 0. D square y by dx square plus p dy by dx plus ky equal to 0. Now tell me, Barkhausen now comes. Barkhausen will say, first don't apply criteria. You first go and buy 2 capacitors or 2 inductors. Then you apply mathematical condition, Barkhausen guide. Nothing is there, no capacitor, no inductor, no circuit is there. Simply A beta 1, A beta 1, A beta 1 means nothing will come. Sine wave will not come. For getting sine wave, first you have to do some shopping. First you have to go to market, buy 2 resistor, 2 RC networks or 2 RL networks or 1 LC. When you connect, you will get this term. Now, if you vanish this middle term, P0, then response is a sine wave. Response is sine wave. Sine wave. So when will you make this P0? This is possible. This is possible with A beta equal to 1. See, A beta equal to 1. Please don't do this. Don't do differential equation and all. First of all, I am not very good at mathematics. If you do differential equation, I will leave the class, right? Differential equation is tough. So in order to make P0, don't do by time domain. Do by frequency domain. We'll do this, only this. Because if you make A beta 1, automatically that condition will make P0. So let us do only A beta 1. Let us, differential equation means one big namaskar I will put. I am not going to do by differential equation because that is time domain analysis. We are going to do only by frequency domain because frequency domain is much, much simpler. In fact, in one of the networks book, I was reading the other day, I think Haytham Kimmerly, I think. So he says that frequency domain analysis is like if you are crossing a river. If you are crossing a river, You are going by boat. If you are going by boat and you are crossing a river, that is frequency domain. Time domain analysis is you are swimming in the river. To cross the river, if you are swimming, is so difficult. So time domain analysis is much difficult than what analysis? Frequency domain. So differential equation will not do. We will simply make A beta 1. Then whatever condition that you get A beta 1 is only to vanish that middle term, and definitely that response is going to be what wave? Sine wave. So I repeat the final summary. There is no input for an oscillator, point 1. To build an oscillator, just if you follow A beta equal to 1, then sine wave will not come. First, you have to go to market and buy some components. What are the components? 2 RC or 2 RL or 1 LC. Then any loss that occurs in this tank circuit, suppose if you put a tank circuit here, an inductor and a capacitor, any loss that occurs here should be compensated by amplifier. Should be compensated by amplifier. That means A beta is 1. What do you mean by A beta 1? A beta 1 means A is 1 by beta. Remember, never forget this. A beta 1 means A is 1 by beta. Very, very important. A is 1 by beta. Which means what? If suppose this tank circuit has attenuated a signal 3 times. If beta is 1 by 3, then you have to design an amplifier equal to 3. In an RC phase shift oscillator, the 3 RC networks will connect. The beta is going to attenuate the signal by 1 by 29. Then what is your job as an engineer? I have a network. 1 by 29 times signal is dying. Then to sustain that signal, I have to design an amplifier equal to 29. In a Wien-Bridge oscillator, RC network at that oscillating frequency will fall. The gain is going to fall by 1 by 3. Beta is 1 by 3. Then A is 1 by beta. That means you have to design an amplifier equal to 3. If your beta is 1 by 3, A is 3. If your beta is 1 by 10, A is 10. If your beta is 1 by 5, A is 5. If your beta is 1 by 29, A is 29. That is what it means by A beta 1. A beta 1 means you have to design an amplifier that is going to be exactly what? That is going to give you 360 degrees phase shift. Okay. Find the frequency of sustained oscillations. Find the frequency of sustained oscillations. Also find the value of Rx. Also find the value of Rx. So this is a gate problem long back for 5 marks, right? But if it is given for 5 marks, how should we do? If it is given for 1 mark, how should we do? Both we will see, right? First we will do by normal method because it is given for 5 marks. And then if it is given for 1 mark, then without doing anything, just by inspection, how will you solve it? Find the frequency of sustained oscillations. Some noise is coming, Venkat. Some noise is coming, as if somebody is clapping. So this is V naught, this is VF. So for oscillations, for an oscillator, I told you any oscillator, only one condition. What is the condition? You have to make A beta 1. You have to make A beta 1. If this is V naught, this is VF. What is A? A is V naught by VF. And for the beta network, input is V naught, output is VF. Beta is VF by V naught. And the third step is A beta equal to 1. A beta equal to 1. So any oscillator, or you can directly go for the third step, right? You can directly go for the third step. So any oscillator, you will have an amplifier and a beta network. Sometimes within the amplifier also you will have inductors and capacitors, right? So you can directly go for the third step also, your wish. Okay. So how to solve this? Step 1. Step 1. What is A? A is V naught by VF. And how do we know who is the input, who is the output? The input and output is decided by this triangle here. Can you see? This is called the arrow. The arrow. The arrow will always tell who is the input and who is the output. That is why the amplifier is always denoted by an arrow, right? You can never say this is input, this is output. For an amplifier, VF is input and V naught is output. That is why V naught by VF. So here you are going to have 9K and 1K, right? So this is going to be 1 plus 9K by 1K, it is 10. If the amplifier gain is 10, the beta network should be 1 by 10, that's all. If you equate the beta network to 1 by 10, then the loop gain, if you make it 1, that's it. Is it done? So step 2 is beta equal to VF by V naught. So who is input to beta network? V naught. Rx, capacitor, inductor, and a resistor. Please, no differential equation, right? Honestly, I'm telling you, I'm not that good at mathematics, so differential equation time domain we are not going to do, right? But we know how to solve it by a criteria called Barkhaussen's criteria. Barkhaussen's criteria is simple. Take amplifier A and beta and equate it to 1. Don't worry about differential equation. So inductor I'll replace by 1 by SC, capacitor by 1 by SC, inductor by SL. This is V naught. Entering current equal to leaving current, right? Or sum of currents that leave a junction is 0, right? Entering current equal to leaving. So tell me case here. This is VF, no? VF. What is input? Input to the beta network is V naught, output is VF. Okay, this is VF. So what is entering current? V naught minus VF by Rx equal to VF by 1 by SC plus VF by SL plus VF by 0.5K. So V naught into 1 by Rx equal to VF into 1 by Rx plus 1 by 0.5K plus S can be written as J omega, omega C minus 1 by omega F. Please, 1 by J can be written as minus J. Remember, 1 by j can be written as minus j. So what is beta? Beta is Vf by V naught. Vf, there is no space here. I will write here. Beta equal to Vf by V naught. So what is Vf by V naught here? It is going to be 1 by Rx by 1 by Rx plus 0.5k plus j omega c minus 1 by omega. So this is the second step. First step. What is the last step? Step 3. Step 3 is Bar-Coson criteria. A beta is 1. So 10 is A, beta is 1 by Rx. Just think how to avoid all this, and just by inspection you have to solve. Just by seeing the circuit, can you tell the answer? 1 by Rx plus 1 by 0.5k plus j omega c minus 1 by omega. Or 10 by Rx equal to 1 by Rx plus 1 by 0.5k plus j omega c minus 1 by omega. Now equate real and imaginary parts. If you equate imaginary terms on both sides, imaginary terms, what do you get? 0 equal to omega c minus 1 by omega L. Omega square is 1 by LC. F equal to 1 by 2 pi root LC. Because omega is 2 pi F. Omega is 2 pi F. This is the frequency of oscillation. If you equate real parts on both sides, then it is 10 by Rx equal to 1 by Rx plus 1 by 0.5k. So you can take LCM here, Rx into 0.5k, Rx 10, what do you get? Rx plus 0.5k. 10 into 0.5, 5 minus 0.5, 4.5. Rx is 4.5 kilo. So this is given for 5 marks in the GATE exam, long back, right? But if the same problem is given for 1 mark, right, how will you, without doing all this, how can you directly tell the answer? Rx is 4, if Rx is any other value other than 4.5k here, then the circuit is not going to produce oscillations, right? The circuit will produce oscillations only when Rx is 4.5k. Rx is 4.5k. In fact, if you ask me to start oscillations, remember to start oscillations, A beta equal to 1 if you do, you will not get sine wave. Because student, when they are doing oscillator experiment, when they switch on, sine wave will not come. The same Rx value, you have to first decrease. When you decrease, say the beta gain is less, amplifier gain is more, then what happens if you keep on increasing or decreasing that Rx? That is why controls is such a fascinating subject. In control systems, they say that if A beta is less than 1, then the poles will lie at LHS of S plane. Then you will not get any sine wave. No sine wave, nothing. So this is for amplifiers. Amplifier. What happens if the pole pair lies exactly on the imaginary axis, A beta equal to 1? Then the structure will burst into a sine wave. What happens if A beta is greater than 1? If A beta is greater than 1, the poles will lie at RHS of S plane. So this is just a plot, right? Don't worry. But to get a pole pair, 2 RC networks or 1 LC network is minimum needed. Then if A beta is greater than 1, then these oscillations are going to grow. So any controls book will tell you that A beta 1 means sine wave will not come. This is from noise. If you want the signal to first develop, what should I do? From noise it has to develop, and after that it has to sustain like this. That means in an oscillator, initially A beta should be greater than 1. And after that, A beta should be equal to 1. But any problem given, we will think that now it is a perfectly sustained oscillator. So I have to make A beta equal to 1 and do the calculation. But after doing all the calculation, when you switch on the supply, oscillation will not come. So slight you have to increase and decrease. You have to first increase that resistor or decrease it finally. So if first you change that resistance, they will get disturbed. Then you will have more gain than attenuation. And after that, you make it to 4.5K. So first directly 4.5K, don't make it. Disturb it above or below 4.5, increase or decrease, and then finally make it come back to 4.5. If you do that, then oscillation will come. Are you getting? You have to just increase, decrease like that. Little. May disturb it. Let the A beta be greater than 1. If it is greater, the oscillations are going to start. But to sustain, it should be 4 point. If you disturb and leave means some nonsense will come like this. Some nonsense waveform will come. It will not sustain. To sustain it, the value should be exactly how much? 4.5 kilo. Okay. So what is the simple shortcut for this? What is the simple shortcut for this? The simple shortcut is, remember, the oscillating frequency is nothing but the resonant frequency. In networks class, you have studied resonance, is it not? Resonance means whenever you have a network like this, the inductor and the capacitor here at resonance is going to act like open circuit. Is going to act like an open circuit. Then it is understood that if you have 9K and 1K here, this is 0.5K and Rx. So now the circuit is kind of a real circuit, right? So whatever gain that you experience, A, this is beta, VF, this is V naught. So now tell me what is A? 1 plus 9K by 1K is 10. What is beta? 0.5K by Rx plus 0.5K. That is going to be 1 by 10. 1 by 10. Are you getting? If A is 10, beta is 1 by 10. Are you getting? So from here, you will get Rx equal to 4.5K. You will get Rx equal to how much? 4.5. So can you see the last step we got? Last step, some factor we got. No? Can you see? So last step, 10 Rx plus 0.5K by 0. So this last step is our only step to solve the amplifier. The last step is only the step, right? Amplifier is 10, beta network should be 1 by 10. So your Rx is 4.5 kilo, right? And you know at resonance, F is equal to 1 by 2 pi tau. 1 by 2 pi tau. What is tau? Tau is either RC, tau is either L by R, and tau is either root LC. So in this circuit, L and C are there. So in the place of tau, what will you write? The place of tau, you're going to write 1 by 2 pi root LC. So this is a simple way of calculating by inspection. Somebody gives for 1 mark, then you can do 0.5K by Rx plus 0.5K equal to 1 by 10. How do you know beta is 1 by 10? Because your amplifier is 10, is it not? So this is a simple way of calculating. Then how is this a positive feedback system? Any system, how do you know whether it is positive feedback or negative feedback? It's very simple. If V naught increases, your VF will increase. If VF increases, V naught will further increase. Any such circuit, it is called what feedback? Positive feedback. Forget about the connections. Whether my output is given to minus terminal, someone is given to plus terminal. Simple. The increase of output, if it further increases, then it is called a regenerative feedback or positive feedback. Forget about where you have connected plus and where you have connected minus, right? If V naught increases, VF will increase. If VF increases, again 1 plus 9K by 1K, your V naught will further increase. Are you getting? So this is called what feedback? Positive feedback.
Road session started na 8:30.
What is this sound?
Actually, doubt session is 8:30 na.
Sir, actually, Venkat sir unmuted all of us, and
What?
some video was also started. Venkat Reddy sir unmuted all of us,
Okay.
and some video also started, sir. That's why
Video.
this.
I am not in that video.
You are also in that video, but many people are there. Me, some Durga, some Abdul, all of them are showing the.
Some video is
No,
started.
today's class is still
Class is still going on,
8:30 na.
sir.
only till 8:30. Is it not till 9?
No.
So the time given in the
It was still
portal
at
was 3 hours.
9.
From
What?
8:30 it will start doubt session, sir.
Today's class is only till 8:30.
From 8:30 it will
No,
start.
sir, not necessarily. You can.
You can
Yeah,
continue, sir.
Yes, sir, you
Yeah.
can continue.
Yeah, a few problems we will do because topic we have just now started, no? Few
Yes, sir.
problems, and
okay.
after that we'll start the doubt session. Huh?
Yes, sir.
Yeah, but Venkat, please let there be only my video. Now you're able to see everyone.
Yeah, unmute all others.
Sir, actually, Venkat sir has unmuted everyone, sir.
Okay.
So it is causing disturbance. If someone do at their end, then it causes disturbance to the whole thing, sir.
Okay. Let me
Please
do
unmute
something
all
from my
of us,
side.
sir.
So it can be done one by one. In doubt session 2, it happens and all of us are unmuted and the one who speaks.
Yeah. No, I came to know how to do it actually.
From
Allow
your
to
end
talk.
you can do it.
Sir, but
Disable.
it will take time, sir, because Venkat sir has unmuted many people, sir.
Or otherwise continue the class, sir. It
Yes,
is
sir.
also best.
Venkat, please mute the students for some time.
Sir, he has unmuted everyone, I think.
Please unmute answers.
So you can continue the class, sir.
Yeah, we'll do some
Sir.
problems.
Yeah, sir. Continue, sir, with the
Okay, sir.
problems. Sir,
I will
please
call
mute.
him.
Yeah, sir, it's better to call him.
హలో నాన్న అందరినీ అన్మ్యూట్ చేశారు, అందరి ఫేసులు వస్తున్నాయంట.
వీడియో కూడా వస్తుంది సార్
ఆ,
అది.
అది వెంకట్కి ఏమైనా చెప్పు. వెంకట్ ఉన్నాడా? రైట్.
Oh, no.
Sir, some unwanted noise is coming.
Yeah. No, I just asked Venkat to log in now and remove that problem. He is logging in.
సార్ డౌట్స్ తీసుకుంటున్నారా లేదంటే క్లాసా?
క్లాస్ ఉంది ఇంకో 10-15 మినిట్స్. అది అన్మ్యూట్ చేస్తారు. అందరికి వాళ్ళ ఇళ్లలో వాయిస్ కనబడుతుంది. ఒక్కొక్కరు చేస్తే డౌట్ సెషన్ లో ఈజీగా అవుద్ది కదా. అందరినీ ఒకటేసారి అన్మ్యూట్ చేసేసరికి అందరి ఇళ్లలో వీళ్ళు వాయిస్లు వినబడుతున్నాయి. అన్మ్యూట్ అందరినీ మ్యూట్ చేసేసి.
మీరు క్లాస్ తీసుకోండి.
థ్యాంక్ యూ. Okay, can you hear my voice now? Can you hear my voice? Okay. Yeah. Now, how do we solve this? As if it is given for 1 mark, right? So, LC at resonance at that oscillating frequency behaves as short circuit. It behaves as short circuit. So, what is VF by V naught? What is V naught by VF? A equal to V naught by VF. It is 1 plus 5K by 1K. It is going to be 5. What is beta? Beta is VF by V naught. It is going to be Rx by Rx plus 10K. So if this is a short, you are going to have a simple divider like this. 10K and Rx. This is VF. And here you have V naught. So Barkhausen criteria, A beta is 1. So 5 into Rx plus 10K is 1. So A beta 1 means A is 1 by beta. So from here, what is Rx? What is Rx? So 5 Rx is Rx plus 10K. What is Rx? So what is the value of Rx? 1 plus 5K by 6K is how much? 6, no? 1 plus 5K by 6K is 6. So this is 6 into. So 6 Rx equal to Rx 5. That means 2K. See, simple. See the ratio here. The feedback resistor here is 5K and the series arm resistance is 1K. So 1K, 5K means what? 2K and 10K. Yes or no? The divider is, if this is 2K and 10K, it is as good as 1K and 5K. So to compensate. So any loss that occurs in the tank circuit is going to be compensated by the amplifier. So if 1K plus 5K by 1 plus 5K by 1K is 6, then the beta should be 1 by 6. So the same ratio you have to maintain. So 2K and 10K. So Rx is 2K. Now this one we have already done. So okay, LC at resonance is an open circuit. And we know the frequency of oscillation. Frequency is 1 by 2 pi root LC. So if you want, you can calculate, you can do the whole circuit, whole step 1, step 2, and then make A beta equal to 1. You will know that the frequency of oscillation is 1 by 2 pi root LC. Okay. So what about this circuit here? The gain V naught by VF V naught by VF is going to be 1 plus 8K by 3K. It is 1 plus 8K by 3K. What is beta? VF by V naught. It is going to be 1K by Rx plus 1K. Am I right? 1K by Rx plus 1K. So the last step is A beta is 1. So now you can have a 1 plus 8 by 3 is going to be 1 plus 8 by 3 is A into beta 1 by Rx plus 1 is equal to 1. So from here you can find Rx in kilo ohms. You can find Rx in kilo ohms, right? So 1K. Yeah. So you can get Rx in kilo ohms. So how much is the value of Rx? How much is the value of Rx? 2.66. K. Now this is a gate problem again for 2 marks, right? It's a very, very simple problem, isn't it? So what is, okay, this is VF, this is V naught. What is V naught by VF? Tell me. Simple gate problem for 2 marks. A is V naught by VF, which is 1 plus R2 by R1. Beta is VF by V naught. It is already given 1 by 6 at an angle 0. So A beta should be 1, which means 1 plus R2 by R1 is 1 by 6. 1 plus R2 by R1 equal to 1 by 6, is it not? Beta is 1 plus R2 by R1 is what? 1 plus R2 by R1 is 6. Beta is 1 by 6. So A beta is 1. Why am I doing it directly? Let me write step by step. 1 plus R2 by R1 into 1 by 6 is 1. So what is running in my mind? 1 plus R2 by R1 is 6. That means R2 should be 5 R1. R2 should be 5 R1. So this is a gate problem for 2 marks, right? Simple problem. If the gain is, if beta is 1 by 6, the amplifier is directly 6. So in a non-inverting amplifier, when will you get 6? If your R2 is 5 times of R1. If your R2 is 5 times of R1, then you're going to get 6 times, right? Okay. Now this is an inverting amplifier. This is an inverting amplifier. Then what is the relationship? What is the relationship? This is V naught. You have VF here. So V naught by VF is going to be minus R2 by R1. So it is R2 by R1 mod at an angle 180 degrees. At an angle 180. But beta is already 1 by 3 at an angle 180. So what is Bar-Cousins criteria? The Bar-Cousins criteria is A beta is 1. You can say 1 or you can say 1 at an angle 0 or 360. 0 or 360. So R2 by R1 at an angle 180 into 1 by 3 at an angle 180 is going to be 1 at an angle 360. So you can equate the magnitude and phase, right? Phase you can add 180 plus 180 is 360. R2 by R1 is 1 by 3. R2 by R1 into 1 by 3 is 1. That means R2 is going to be 3 times of R1. So that is understood because inverting amplifier, if beta is 1 by 3, then your amplifier gain should be 3. That means minus R2 by R1 is 3. That means R2 is 3 times of R1, right? R2 should be 3 times of R1. So at resonance, what will happen to an LC network? It has to give you, it should not stop the signal flow, is it not? So if it is in parallel, it is going to give you high impedance. If it is in series, it is going to behave as low impedance, right? So LC at resonance is going to be short for low impedance and high for. So this you will study in networks, parallel LC network and series LC, right? Resonance. Now, how do you get the frequency of oscillations? How do you get the frequency of oscillation? You can directly go for the third step. What is the third step? The loop gain should be equal to 1. The loop gain should be equal to 1. What do you mean by loop? Loop means you start at one point and you come back to the same point, right? So if this is V1, this is V2, and this is V3. So what is loop? Loop is V2 by V1 into V3 by V2 into V1 by V3 should be 1. V2 by V1, V3 by V2 into V1 by V3 should be 1. What is V2 by V1? V2 by V1 is 1 plus capacitors are replaced by 1 by SC, 1 plus R2 by R1. It is V2 by V1. What is V3 by V2? It is minus R2 by R1. Minus R2 by R1. What is V1 by V3? What is V1 by V3? This is V1. And here you have V3. If you want, I will draw it here. The input is V3 and the output is V1. 1 by SC and R. So what is V1 by V3? It is 1 by SC by R plus 1 by SC. This is 1. So this is going to be 1 by SCR, 1 plus 1 by SCR, which is SCR plus 1 by SCR, the first term. Second term minus 1 by SCR. Third term is 1 by 1 plus SCR. So very simple, 1 plus SCR, 1 plus SCR gets cancelled. Minus 1 equal to S square C square R square. Put SC equal to J omega. Put SC equal to J omega or S square equal to minus omega square. So therefore, minus 1 equal to S square C square R square can be written as minus omega square C square R square. So what is omega? It is 1 by RC or F equal to 1 by 2 by RC. This is the frequency of oscillations. So how did we get any problem? Only one condition, Barkhausen criteria. What is the Barkhausen criteria? Loop gain should be 1. If you have only amplifier and beta, A beta equal to 1. What happens if you have a network where there is A1 here, there is A2 here, and there is beta here? When will this be an oscillator? Loop gain means A1 into A2 into beta should be 1. What happens if A1, A2, A3 and beta are there? When is that an oscillator? A1 into A2 into A3 into beta should be equal to 1. That means the gain multiplied in the loop is called the loop gain. How many gains are there in the loop? 1, 2, 3. The 3 gains are there in the loop. You multiply them, it's called the loop gain. The gains in the loop. So if you just substitute, you got minus 1 equal to S square C square R square, or your omega equal to 1 by RC, right? Okay, so shall we stop here? We will see the Wien bridge and other oscillators, Colpitts, Hartley tomorrow. And after that, tomorrow's class, what time is tomorrow's class? So tomorrow we will meet at 2 o'clock, because please, tomorrow is the last day, right? So you have to kindly bear with me. So tomorrow we'll meet at 2 o'clock, right? And we have to see feedback amplifiers also. So tomorrow the day will be a little long. So we'll meet at 2 o'clock tomorrow, right? So if there are any doubts, you can ask me now.
Hello,
Hello,
sir.
sir.
Hello, sir.
Sir,
12F.
sir, yes.
12F, huh?
Hello, sir.
Yes, sir.
Tomorrow class is 2 to 8, sir?
2 to 8. Is that okay?
Okay.
Last day, no?
Yeah.
Yes, sir.
Kindly
Okay,
bear,
okay,
no?
sir.
Please.
Yeah, definitely, sir.
After that, you
Definitely.
will not see my face. Okay.
No,
Yeah, anyways, you can contact me over WhatsApp. Yeah. Which question is that? 12F?
12F. Yes, sir. So why are we calculating gain bandwidth product there? I didn't get. Is that a certain parameter or just
No. See, you know that the gain is high in an op-amp, but the bandwidth is very small in an op-amp. So somebody who sees the amplifier which is having high gain and no bandwidth, he might first think that, is this circuit really useful? Because you have an amplifier with such huge gain. See here, this is the gain of the amplifier. Can you see here 10 power 6?
Yes, sir.
So the bandwidth is very small, only 10 radians per second. So with this, what can you build an audio amplifier? An audio amplifier
Yes.
needs at least 20K, no?
Yes.
So the first impression you get is this is useless. Op amp is useless. But after giving negative feedback, the whole story changes. The gain will reduce and the bandwidth will improve. This gain bandwidth product is given in the data sheet. When you buy an op-amp, no, op-amp manufacturer himself will give gain bandwidth product because he's giving you a playground. He's saying that only within this gain bandwidth product, which is the frequency reach of the amplifier,
Okay, you can bargain between gain and bandwidth.
So if you're decreasing gain, increasing in gain, this is the bandwidth that you get. So that's your playground. You cannot play more than that, above that.
Okay. And also, so oscillation concept comes when the oscillator is trying to find a perfect output.
Where in oscillators you are saying, or frequency compensation?
So how does this oscillator concept comes into picture? That's what I'm not able to.
Oscillator, this is intentionally, we want a sine wave in our day-to-day life. Suppose you want to build an inverter circuit in your house. For 50 hertz sine wave we need, no? If you open that inverter, we'll have an oscillator. So oscillators are good when we are designing an inverter, yes, because we want sine wave. That sine wave we will give it to a step-up transformer and step it up to 230 volts, 50 hertz. So once power goes off, we can have fans and tube lights, illuminated. So sine wave we need. In which topic we need? Oscillator topic. But if any amplifier, if it oscillates when we give feedback, then we have to stop him from doing it. That is called the frequency compensation. We have to
Say
put
an
one
amplifier, how does this oscillation comes
Every
in?
amplifier will oscillate. Every amplifier is unstable. Any circuit in this world, if you give feedback, it is unstable. Why? Because they will pick some frequency which is having 360 degrees phase shift in that loop. If you ask me who will give you 360 degrees phase shift, any circuit which has more than 3 capacitors will give you, which is 3 or more. With only 2 capacitors, what circuit will you design? 2 capacitors means 1 transistor you have to connect. With 1 transistor, can you design any circuit? You cannot design any circuit. Millions and millions of transistors will be there. And every circuit has junction capacitor. The moment you give feedback, pakka it is waste. All circuits are waste if you give feedback. But if you compensate that circuit, frequency, what is frequency compensation? The circuit should feel that as if there is only 1 capacitor in it.
Okay.
Then how it will feel? That means you have to still make it slow. You have to make it dead slow. That is the trade-off. That is a trade-off. See, if you want to use a circuit, you have to decrease its bandwidth, then only you can use it.
Okay.
But after buying that circuit home, then I am giving you one product. Boss, gain is very high, bandwidth is very less. It is stable. Now within this product, you adjust the gain and bandwidth. That's all.
And also this input voltage criteria, I didn't get it. Why are we considering it?
Which input voltage criteria?
So in previous, yesterday's lecture.
In yesterday lecture?
Input offset voltage, sir.
Offset voltage. Yeah, there is a
Yes,
shift
sir.
in that characteristics, no?
Because
The characteristic does not go through the
non-ideality.
center. See, offset means what? If the error is called an offset, some DC voltage error is called an offset. That offset we have to compensate by connecting. If there is negative, you have to put one positive and do the analysis. It's only for analysis purpose.
Okay.
See, we are
And
not
sir,
going to make an ideal op-amp there. It's not possible.
yes.
We are only calculating. See, we are saying no, error has come. For that error calculation, we are doing this.
Okay. And sir, in questions when we are given VOS, some value of
He
VOS,
will give only positive values, and whatever value he give, you just use it to the non-inverting terminal. That's it.
yes, sir, I'm finding out that if only VOS is given, offset voltage, and no IP or IN, that
Then you will get normal, no, 1 plus RF by R1 times of VS.
so then we don't have to consider IP or IN.
No, IP and IN you consider, but that is 0, no? If IP is exactly IN or IP and IN are not there, then your IP minus IN is 0 only.
Okay, if it's not mentioned in the question, then we
If
should.
it is not mentioned, there is already we are calculating one error. Why are we to worry about other errors? But if he gives you IP and IN as well as VOS, then both the errors have to be added.
Okay. Thank you so much, sir.
Yeah.
Hello, sir.
Yes.
Hello, sir. 5F, sir.
Huh?
5F.
5F, huh?
Yes, sir.
Yeah.
Sir, 6F also.
Yeah.
Sir, can you explain the V1 and V2 once again, sir, please?
Yesterday I told you, no, any signal, any arbitrary signal can be represented as to having a differential component and a common component.
Okay. Yesterday. Okay, sir.
Yesterday I told V1 can be written as V1 by 2 plus V2 by 2 plus V1 by 2 minus V2 by 2.
Yes, sir, you told.
That is a
I forgot.
representation.
Sir, and you told that it will become slow now, sir.
Which one will become slow?
The signal. 1 minute.
You are talking about today's frequency response or slew rate or what?
Frequency compensation, sir.
System will become slow naturally, but your signal is still slow, no? Distortion
Yes,
will
sir.
not be there. Don't worry.
If it will become slow, it will not affect. It should be fast, no, sir. Actually.
It should be faster, but it is slow. Your signal is still slow, I'm saying.
Yes, sir.
See, it is something like I have two students in my class, two group of students. This batch student and another batch student. Two students are there. Now, in this batch student, all the students are sharp. All the students are sharp, for example. In another batch student, all the students are slow. Now, what I'm trying to say is, even if you take the other batch students and add all the time, how they solve the problem, even if you add all the person's time, no, still they cannot be equal to one student in this class. The most slowest student in this class. Suppose in this class, there are 100 students. And you have put one additional capacitor, one additional fellow you have put. He is very, very slow. He is still slow. But still, the signal that you are connecting is still further slow. The slew rate of the system is already slow, but your signal is still slow. That is why no distortion will come. Are you getting?
Yes, sir.
Are you getting? See, you are saying already capacitors will give delay. But now I put an additional capacitor. I made it still slow, no? When I make it still slow, I am going to get something called slew rate. What is slew rate? dV naught by dt max. But this value is still high when I use any signal input. The signal input is having still larger time scale. So no distortion will come.
Okay.
See, delay means what here? Previously, there will be 0.1 picosecond delay. After connecting this capacitor, you will make it 10 picoseconds delay.
Yes, sir.
Then the signal that you are connecting will still be slow, so no distortion is going to come. What is your doubt? Are you worried about making it slow? If you don't make it slow, it is unstable, no? What you will do? If you cannot use it. See, you will have a fast system, but even without input, sine wave will come. What you will do with that system? That system is said to be unstable, no? An unstable system, what you will do here, even if it is fast? Are you getting?
Sir.
Yeah. Anybody else? Next.
Sir,
Yeah.
sir, in today's class you told about some phase shift, na sir? 180, 360.
360 degrees phase shift should be there for sine wave to produce. If negative feedback is already giving 180, then the forward path should give additional 180. Yeah. What is your doubt?
That's all. Okay.
Forward path is there, no? See, 180 means simple here. I am having so many sine waves. Suppose I am having this sine wave, I am having this sine wave, I am having this sine wave, I am having this sine wave. In this, which is a danger sine wave for me? Which is a danger sine wave for me? Suppose I am giving an op amp, the delay offered by this op amp is suppose 1 millisecond. 1 millisecond delay from here to here. In this sine wave, there will be half period which is 1 millisecond, some fellow. This is danger. You know why? When you apply that signal, the signal half delay and the system delay both are matching. Then this signal, when it goes to the output, it will flip by 180 degrees. Then you will give negative feedback for it, again 180 degrees. So what will happen? By the time you go for the next iteration, it would have completed one full 360 degrees and with some gain, right? The gain is high. Gain is high. Then it will keep on going like this. Then it is unstable. They say it is unstable. There should not be even a single frequency where A beta is greater than 1 and the angle A beta equal to 180 degrees. Then the system is unstable. Any control system book will tell you this. So who is going to give 180 if your system has got 3 capacitors or more? Third order system or more means finished. You have to throw. Are you getting?
Yeah, sir. I get it. Okay.
Yeah. First order means very simple, sir. First order 0 to 90 degrees phase shift maximum. 0 degree, 10 degree, 20 degree up to 90. 2 capacitors. Second order system means 0 to 180. Third order system 0 to 270. In between 0 to 270, won't you get 180? Is 180 less than 270 or not?
Yeah.
Yes, that means finished.
Yeah.
Circuit is gone. It is going to oscillate at some frequency.
Okay.
Next.
Thank you, sir.
Yeah.
Sir,
Next.
your 360 degree.
Huh?
Hello.
Hello.
Angle
your
of A
voice-
beta here you have written 180. Hello.
Yeah, tell me.
Sir, here you have written A beta is 180 degree. Angle of A beta is 180 degree.
This is
Sir,
A bit B.
but-
The additional 180 is given by negative feedback, no?
Yes, sir.
Additional 180 is given by negative feedback. Forward path should not be more than 180.
Okay.
Are you
So
getting?
total is 0 degree.
See, simple,
Yes,
sir.
So,
The closed loop stability, remember in controls you will study this. The closed loop stability is always judged by taking the open loop transfer function for 180 degrees.
okay.
Are you getting? You have a closed
Yes,
loop
sir.
system. How do you know whether it is stable or unstable? Already 180 degrees you are giving by feedback, unity gain. So you have to take the
Yes.
open loop transfer function, and with that open
Okay.
loop transfer function you should see is there any frequency which will give 180 and the gain is greater than 1. Then finished. That system you have to throw.
Okay.
By connecting a large capacitor, you will make A beta equal to 1 at an angle A beta is 120 degrees. Then you will have a margin of safety. The margin of safety is called phase margin of 60 degrees. 741 manufacturers have 60 degree phase margin. Are you getting?
Yes, sir.
Yeah. Study, please study controls, sir.
So-
Control systems, you will study
Okay.
about the dominant pole and all that, right?
Yes. Sir,
Yeah.
21.
21. Your voice is getting cut.
Hello.
Yeah.
So 20th, sorry. 20th. The unity gain frequency graph. Yes.
Yeah.
Here one indicates the 3 dB frequency or
One indicates
3
the 0 dB
gain
line.
or what?
0 dB. This is 120 dB. 1 means 0 dB line.
Sir, you have taken 10 power 6 by root 2 for calculating omega 3 dB.
Yes,
But
yes,
here
yes.
you have taken 1 by root. Sir, why not 1 by root 2? Like, I didn't get why.
Acha, you want 1 by root 2, then that is omega 3 dB, no? If A is, acha, you want this, you want A equal to A naught by root 2.
Yes, sir.
So if A is A naught by
For
root 2,
calculating-
then omega will be omega 3 dB. Yes. So this is your omega 3 dB. At omega 3 dB, when your omega means x-axis, when omega is 0, you will get 10 power 6, no?
Oh, yes.
Are you getting what I'm saying?
Yes, sir. Yes, thank you.
Yeah, let me write it like this for you. See here. A equal to A naught by 1 plus root of omega by omega 3 dB whole square. Can you see?
At least I will
Yes.
pay my.
Yes.
Have you understood?
Yes, sir.
Omega is 0, A is A naught. Omega is omega 3 dB. A is going to be A naught by root 2. Omega is A naught into omega 3 dB. If your omega is A naught into omega 3 dB, then your A will be equal to 1.
Huh?
Yes, sir. Yes, I got it.
Are you getting?
ये अभी नहीं है
That
ना
is
ये?
why this
Yes, sir.
frequency is called
हाँ.
unity gain frequency.
Okay.
नहीं वो एनरोलमेंटेड अभी सितंबर
Yeah.
वो ओटीपी नहीं है.
Hello, sir.
Yes, sir.
Yes.
Good evening, sir.
Yeah.
Sir, I'm having doubt in yesterday's class.
Yeah. Tell me.
Sir, can you please open, sir?
9 F F 9 F 1.
Sir, what is VCM, sir?
What is
VCM.
common mode gain? The gain due to a common signal.
VCM is voltage due to common signal, sir.
VCM is the voltage due to common signal. Yes. Arey yaar, my kids have done something here. Okay. Have you understood?
Oh wow.
I'm having
Yeah.
Hello.
Yeah. Tell me. Can you hear my voice?
Sir, is it possible?
Your voice is
Breaking, sir. Voice is breaking.
is my voice breaking?
No, your voice is not breaking, sir.
Yeah, the student's voice is breaking.
Yeah.
Okay, anybody else?
Sir,
Yeah.
hello sir.
Yes.
Sir, if we add 0 to the open loop transfer function, the stability increases, sir. How,
See,
sir?
yes, what you have said is correct. There are, to create stability, there are actually 3 methods. One is you can decrease the gain. 2, you can add a pole. Or you can add a 0 also. Yes, you are right. Absolutely right.
Sir, how, sir?
Arey yaar, complete controls now we cannot do, no? We can
Just
have a, you see in the shunt arm you can have an extra capacitor. In the series arm we can also have an inductor also. We can do that, but now it takes time, no? Then the transfer function, it is simple, but in op amps we are not going to add 0 in a 741. We are going to only add a pole.
Okay.
So all these compensation techniques you will study in controls. Okay.
Okay, sir.
But what you said is correct.
Okay.
You can even add a 0. Yes.
Yeah. Okay.
Next.
Oh my God, voice.
Hello, sir.
Yeah.
Hello, sir. Good evening, sir. Sir, can you go to 23, sir? Today's class 23. Today's class, sir.
Yeah.
This is actually. This only, sir. Sir, in this you are written DC gain, sir. DC gain equal to 1 plus R2 by R1.
Yes.
Sir, while doing non-inverting terminal, we are writing V naught equal to 1 plus R2 by R1 into V in, sir.
Yes. This is V dot by V.
Sir, this
Gain
is
means.
Sir, in the first of our class, we are written non-inverting 1 plus R2 by R1 into V in, sir.
Yeah. See, there is a difference between output and gain. Gain means V naught by V in.
Yes,
Output means V naught is equal to 1
Yes, sir.
plus R2 by R1 times of V in.
I understood this point, sir.
Ah.
What I'm asking is, In the initial days our class, you are written V naught by Vn equal to 1 plus R2 by R1 only, sir.
Yeah.
The AC gain, this is DC gain.
No. Whatever might be the input, whether it is AC or DC, this is the gain. But what I'm saying is, this is the gain strictly for a non-ideal amplifier. This is a gain for low frequency, zero frequency. As the frequency increases, the gain will decrease because inside there is a capacitor there. But there, in initial classes, we have always treated op-amp as ideal. The ideal, there is no DC, AC. Whatever you give 1 plus R2 by R1, you will get.
Sir, another doubt, sir. In frequency compensation, we are using one capacitor in the IC, na, sir.
Yes.
Sir, why only that capacitor frequency compensation, sir? Because due to Miller only.
No. We are additionally putting that capacitor in a Darlington pair to create a Miller effect.
Light on right.
Oh.
Without that capacitor, system is unstable. What will you do? It is oscillating. Can you sell?
No, sir.
No, you cannot sell. But even if somebody buys it, they have to connect that capacitor at a
Externally.
port. One port it is provided. That is called external compensation.
External.
And he has to connect it, keep on increasing. It's all headache, no?
I see.
They thought, let us connect for a circuit that is a worst circuit in electronics. Who is a worst circuit? The circuit with the maximum loop gain. Who is a circuit with maximum loop gain? Buffer. If you take a buffer and you compensate for a buffer and you sell that IC, anybody who takes that IC, he will connect adder circuit, subtractor, anything he connects, it will never oscillate. Because it has not oscillated for A beta equal to A for buffer. That is why whenever you study compensation techniques, you should always study unity gain feedback with unity gain feedback. Because if a circuit works for unity gain feedback, it will work for every circuit.
Okay, sir.
Because I don't know what for you will use that IC. No? You might use for adder, somebody might use it for integrator, we don't know. But can I say for adder it will work, for integrator it will not work, it will oscillate? So no. So we have to compensate it for the circuit which has got the maximum loop gain. That is why whenever you are doing compensation techniques, we will always do it for unity gain feedback. Complete control systems runs on what feedback? Unity gain.
Sir, here the value of capacitor is very, very less because due to Miller it is.
It is large because fabricating capacitors is difficult, no?
I see.
That is why we put that.
Sir, for fabrication of capacitor, we have level shifter, na, sir. In differential amplifier, we have seen.
See, we are not making capacitors there. We are doing only the job of a capacitor.
Job of capacitor. Okay,
Blocking DC we will do. Capacitor here we are doing.
Okay, sir.
Capacitor
Sir,
means
another
two
doubt.
plates separated by dielectric.
Dielectric. Sir, another doubt, sir. Sir, in yesterday we have done non-idealities of op-amp, na, sir. Sir,
Yeah.
in that we are using one concept CMRR.
Yeah.
Sir, in that CMRR you are using virtual ground concept, na, sir.
CMRR today problem we have done. Virtual ground.
Yesterday also you did some problems. Today
I have
only,
not done
today.
yesterday. Today only we have done.
Today
CMRR.
only, sir.
Yeah.
Sir, you are using a virtual ground concept, na, sir, today.
Yes. Because the gain is high.
But we are considering a non-ideal.
See, when I am talking of CMRR, all other parameters are ideal only. If I am talking of input offset voltage only, all other parameters are ideal only. We have to alleviate the problem one by one, I told you yesterday. You have to take only one non-ideality. See, one non-ideality means only one thing you can cripple. You can only say, if op-amp is deaf, what can we do? You cannot say, no sir, op-amp was paralyzed before. Previous case it was paralyzed, but now it is deaf. Next case it will be dumb. Next case he will not have one hand. Are you getting? Then how are you going to manage the situation? That is more important. All the problems you cannot put it for one op-amp. You have to alleviate the problem one by one. When I'm talking about CMRR, its slew rate is infinite. If I'm talking about its offset voltage is 0, its current offset is 0. Everything is, are you getting? Gain is infinite, like that.
Infinite.
Yeah. Only one problem you have to alleviate. Because 2 problems, 3 problems if you give, then I have to apply superposition theorem on it.
Okay, sir. Sir, another doubt, sir. We are talking about oscillations now, sir.
Yes.
Sir, in the lab, we are using function generator to generate a sine wave.
Yes.
This oscillation concept is used on
100%. 100% inside there will be one. If it is an audio frequency, it will be a Wien bridge oscillator. If it is a radio frequency, you will have Colpitts or Hartley.
Colpitts.
Yes.
Okay, sir. Thank you, sir.
Yeah.
Sir, your teaching is really awesome, sir.
Thank you so much.
Hello, sir.
Yes.
Good evening, sir. Hello.
Yeah. Good evening. Tell me.
Sir, can we generate oscillations using negative feedback?
See, amplifier, a linear amplifier with negative feedback is needed to build an oscillator of positive feedback. Let me repeat my statement. Every amplifier in an oscillator will have negative feedback. When I need an amplifier A beta should be 1. If I need an amplifier A, that means there should be negative feedback. But such negative feedback amplifiers, if I connect in a loop, the overall feedback should be positive. It is something like this. The last problem we have done. Can you see the last problem?
Yes.
In the last problem, I have taken linear amplifiers, 2. One is a non-inverting Miller integrator. The other one is an inverting Miller integrator, both with negative feedback.
Yes, sir.
But when I connect an RC network, only at a particular frequency, this is a marginally stable system, only at a particular frequency, f equal to 1 by 2 pi RC, what is happening is, if V3 increases, V1 will increase. If V1 increases, V2 will increase. If V2 increases, V3 will increase. This whole system is positive feedback.
Yes, sir.
But if you remove one section and put in your pocket, suppose V2 by V1 you remove, and you say, what is the feedback? There is a feedback called negative feedback. Can you see there's a negative feedback here?
Yes, sir.
Can you see there's a negative feedback?
Yes, sir.
But this is not oscillator. This is not oscillator. This is oscillator.
Okay. The dominant one should be the positive feedback, sir, right?
The overall, the feedback experienced by all the signals here, not by VD. You are seeing VD only, no? If V0 increases, this will increase, VD will decrease. There is a feedback with respect to VD. That is negative feedback. Looking at op-amp VD is not oscillator. Looking at V3, V2, V1 is an oscillator.
Okay, sir. Got it, sir.
Yeah.
Sir, and another doubt, sir. Sir, I have doubt in relation between speed, bandwidth, and delay, sir.
Yeah.
Can you please tell me this relationship?
Time is always R and C, no?
Yes, sir.
Speed is slew rate, dV naught by dt. It is I by C.
Okay.
Bandwidth is 1 by tau. That's all. 3 things.
That means if delay increase, bandwidth will reduce, sir.
Obviously, if a delay increase means what? It is slow. When it is slow, the amplifier will have an ability to amplify low frequency signals, but not high frequency.
Okay, sir. Okay. Sir, another one.
Yeah.
Sir, when I was solving a problem, it is given a forward resistance of a Zener diode, sir.
You take in series, what is there?
No, sir. But the Zener was in breakdown, sir.
Okay, that breakdown voltage in series with the resistor you have to connect.
Sir, that is forward resistance, sir. So, should we consider that in breakdown also? That resistance?
Yeah. You have to replace the Zener voltage, Zener with a voltage source in series with resistor.
Okay, sir. Okay. Thank you, sir.
Yeah.
Hello, sir.
Yes.
1F page number.
Enana? 1? 1F.
Yes, sir. Sir, in this V out by VP equal to, this is 1 plus R2 by R1.
1 plus R2 by R1. Yes, 1 plus 9K by 1K is V0 by VP. Yes.
This formula for non-inverting, no, sir.
Yes, this is a formula for non. This is also non-inverting, no? V0 by VP is non-inverting.
V0 by for values non-inverting 1, 9, 10 K. No?
Yeah, this is non-inverting. This is VP here.
Yes, sir.
Here there is 1K and 9K. 1 plus 9K by 1K is V0 by VP. Yes. But VP by V1 is this divider. So do you remember voltage division formula?
Yes, sir.
You can apply this for VP by V1.
Sir, for VP by V1 also same, sir.
VP by V1 voltage division rule.
Okay, sir.
Can you see here voltage division? Can you see this network 1K, 10K?
Yes, sir.
Can you see the cursor?
Yes, sir.
R2 by R1 plus R2 voltage division.
Okay.
Yeah.
Sir, in 1 plus R2 by R1, here only why should I apply for CMRR and oscillator, sir? Previous one not applied, sir. Input offset and infinite gain.
This topic is about CMRR. When we are considering CMRR, we should not discuss about offset and current. Offset voltage, offset current. We will have to consider only one problem at a time. Are you getting
for CMRR and oscillators only we should apply this one.
CMRR and oscillator. Oscillator is some other topic, no? CMRR is the ratio between the differential gain to the common mode gain. Okay. Next.
Sir, page 19F.
Yeah.
Sir, in this you applied direct shortcut, no, sir. Also not enough.
Shortcut, don't do all this I'm saying. Shortcut means just this formula you have to apply.
FT
equal to A0 into F3. That's all. FT is already given. Gain you have to find 1 plus R2 by R1. F3 dB you can find. That's all. What is it? Gain bandwidth product is FT.
For next problem, 20F. Sir. 21F. Next problem. Sir, in this CLTF equal to, we should apply total gain in this.
Yeah, this is closed loop gain by closed loop bandwidth, no? This gain is closed loop.
Closed loop. Okay.
Array, yeah, closed loop. Pen is not writing. This is closed loop gain. This is closed loop bandwidth.
Sir, 26F.
Yeah.
Sir, this problem is not understood now. Single stage, two stage, three stage.
See, if you want all the gain in a single stage, then you can have 999K and 1K. Gain will be 1000. But what is the bandwidth? Bandwidth is only 1 kilo, no?
Yes, 1 kilo.
If you go for 2 stage of 1000, then each stage is going to be 31.63 into 31.63. Because 31.63 into 31.63 is 1000.
1000.
So you want 2 stage to give 1000, no? So 31.63 into 31.63 is 1000. So if you want 1000, then you have split the gain into 2 stages. But what is the bandwidth here of single stage? 31.63K. Same formula we have used. FT equal to G into F3 dB. Can you see this?
Yes, sir. Again, we applied 3 stages.
2 stage itself is enough because 20 point something we got, no? 20.2K something we got.
Sir.
Our main aim is only 20K. See here, can you see 20K here?
20K.
We got, 20K. If you, I'm just saying, if you go for 3 stage, you'll get up to 50.9K. But not needed. Why you will waste money? Yes, sir. Why go for 3 op amps? 2 op amp is enough.
Sir, in oscillators, F equal to 1 by 2 pi RC. We wrote directly, we derive total.
Yeah, loop gain. Loop gain equal to
direct
1. Yes. Directly you can take the loop gain equal to 1 in any problem. Okay,
Sir,
next.
last problem.
Yeah.
Last problem. Sir, in this loop gain equal to 1, so V2 by V1, how you take V2 by
This is
V1,
this
V3 by V2?
capacitor you take R2, resistor you take R1 and do 1 plus R2 by R1. Non-inverting amplifier formula 1 plus R2 by R1.
For V3 by V2?
Inverting amplifier minus R2 by R1.
Oh, okay, sir. Understood, sir.
Okay.
Hello, sir. Hello, sir.
Yeah.
Sir, actually, I lost my connection, sir. Sir, I have doubt in yesterday's class, sir.
Yeah, tell me.
Sir, page number 22F, sir.
I'm not able to find that page here. Tell me what is there in that.
Okay, sir. There actually in one problem in inverter, sir. In integrator, sir, you have directly took the formula, sir, like V0 is equal to V1 minus V2 into AD, that thing, sir. Sir, there we can apply superposition theorem also, right?
Anything you can apply. Yes, you can apply.
Okay, sir. And in one more problem, frequency, actually we are getting answer in kilohertz, sir. One problem, but you have written only in hertz, sir. Like, which one is I am getting?
Which problem?
In yesterday's class, sir.
In kilohertz, sir. Yesterday we have done only offset voltage, offset current calculation.
One frequency we will get, sir, in that problem.
Slew rate problem, yeah.
Yes, sir. Their frequency I am getting in kilohertz, sir.
Kilo is correct.
Okay, okay, sir.
Yeah.
And sir,
Hello.
Sir, CMRR, what is CMRR, sir?
It is the ratio between the differential gain to the common mode gain. Differential gain means signal. Common mode gain means it can be noise or DC. DC we have to eliminate, signal we have to amplify. That is why I have given 5 volt and 3 sin omega t millivolt. 5 volt is cancelled, no?
Yes, yes.
Only 3 sin omega t is amplified. So your what you call instrumentation amplifier has good CMRR.
Okay.
Yeah.
Okay, sir. Sir, and one more doubt is, sir, and that CMR derivation you have written, right, sir? That is not that much important, no, sir. Only.
No. Formula you remember, yeah. A1 minus A2 by 2 times of A1 plus.
Okay, okay, sir. And sir, in today's class, at last problem, sir, that gain you have directly calculated, sir. Today's class.
Today loop gain we have taken, no, for all the stages. 3 stages are there.
Sir, can you open for today's class?
Yeah.
Yes, sir. Actually, that frequency we have formula, sir. Frequency 3 dB. Hello?
For this you have to calculate loop gain. Oscillator you are saying, no?
No, sir. Directly you have said the gain, sir, for 100. For if
Gain bandwidth product is given, no? What more do you need? Gain bandwidth product is unity gain frequency.
Yes, sir. Here, yes, sir. In this problem. That,
this one, no?
Yes, sir.
Gain bandwidth product is given by examiner, FT. Bandwidth we have to find. Directly gain bandwidth product is unity gain frequency.
Okay, okay, sir.
Gain bandwidth product with feedback or without feedback is going to remain unchanged.
Okay, okay.
Bandwidth can calculate from here.
Okay, in these type of problems, they will ask F3 dB and gain, sir.
FT gain you can find from circuit now 1 plus R2 by R1.
Okay, okay.
Gain is from the circuit. FT is given. Bandwidth you have to find. Bandwidth equal to FT by gain.
Okay, okay, sir.
Yeah.
Okay, sir. Sir, actually, I'm having one doubt, sir. We have one 3. Can you please draw, sir, the diagram?
Yeah. Tell me. You can send me on WhatsApp, no?
Sir, actually, I have two voltages, one parallel, sir. One is 3 volt and one is 7 volt, sir.
Okay.
Sir, the which voltage it will across a drop?
Smoke will come from circuit. You should never connect. What is the current I? I equal to 7 minus 3 by 0. Infinite current will flow. There should always be a resistor in every loop.
Okay, okay.
This is violation of Kirchhoff's law. Circuit will not exist. These type of circuits you should not connect in lab.
Okay.
Only on Diwali.
Okay. And if there is a resistor, then it will.
There is a potential difference. Suppose you put a resistor 1K, 7 minus 3, 4 by 1K, 4 milliamp will flow.
Sir, and voltage, sir, voltage at if I want to take voltage, sir.
Where you want to take? Here if you take 7, here if you take 4, here if you take 3, algebraic sum is 0.
Okay, okay. Thank you, sir.
Yeah.
హలో
Yes.
గుడ్ ఈవినింగ్ సార్.
Yeah.
సార్ మనము ఇప్పుడు ఆసిలేషన్స్ కావాలంటే ఏ బీటా ఈజ్ ఈక్వల్ టు 1 కండిషన్ సాటిస్ఫై అవుతూ ఎల్సి సర్క్యూట్ ఉండాలి కదా సార్.
ఎల్సి గానీ 2 ఆర్సీలు గానీ 2 ఎల్ఆర్ గానీ ఉండాలి.
ఓకే సార్. అప్పుడు మనకు సైన్ ఆసిలేషన్స్ వస్తాయి కదా.
లూప్ గెయిన్ ఫస్ట్ గ్రేటర్ దెన్ 1 చేయాలి. దాని తర్వాత లూప్ గెయిన్ ఈక్వల్ టు 1 చేయాలి. ఈక్వల్ టు 1 ఉండాలి లూప్ గెయిన్.
ఓకే సార్. అంటే ఇప్పుడు మనం ఒకవేళ స్క్వేర్ వేవ్ గానీ ట్రయాంగిల్ వేవ్ గానీ అప్పుడు ఇన్పుట్
అది హార్మోనిక్, అది వేస్ట్. అది ప్లస్ వి సాట్ మైనస్ వి సాట్ కింద ఉండాలి. అది స్క్వేర్ వేవ్. స్క్వేర్ వేవ్ అంటే ప్లస్ వి సాట్ గానీ మైనస్ వి సాట్ మధ్యలో ఉంటుంది అంతే. ఇది సైన్ వేవ్, హార్మోనిక్ యాక్షన్. ఇది హార్మోనిక్ యాక్షన్ కావాలి అంటే సెకండ్ ఆర్డర్ ఫంక్షన్ ఎస్ స్క్వేర్ టర్మ్ కావాలి.
ఓకే సార్. అంటే ఇప్పుడు రెక్టాంగిల్ ట్రయాంగిల్ అనేవి
రెక్టాంగిల్ అవన్నీ అంటే ఇప్పుడు ఆసిలేటర్లు 2 టైప్స్ అన్నమాట. ఒకటి రిలాక్సేషన్ ఆసిలేటర్, ఇంకోటి హార్మోనిక్ ఆసిలేటర్. ఇవాళ మనం మాట్లాడిందంతా హార్మోనిక్ ఆసిలేటర్స్. నువ్వు చెప్పేది రిలాక్సేషన్. ప్లస్ వి సాట్ మైనస్ వి సాట్ దగ్గర ఉండేది అస్టేబుల్ మల్టీ వైబ్రేటర్ అంటారు దాన్ని. ఆ అస్టేబుల్ మల్టీ వైబ్రేటర్ సర్క్యూట్ మనం ఆల్రెడీ చేసాం.
ఓకే సార్. ఓకే, థ్యాంక్ యూ సార్.
యా.
Hello, sir.
Yes.
Sir, can you draw the diagram, sir? Actually.
Just now you told, no? 7 volt, 3 volt.
Yes, sir. Actually, I was missing one thing, sir, in that. Sir, there is a 3 volt, sir. And 7 volt is parallel to a 3 volt. And across the 3 volt, there is a resistor, sir.
Are yaar, 7 volt parallel with 3 volt, you should not connect.
No, sir. Across the 3 volt, there is a resistor, sir.
Across is in that loop there is no resistor, no, between 3 and 7. That is violation.
There is resistor, sir.
Across it is there in that loop series.
Yes. There is resistor, sir.
Hey, my dear, this is 3 volt.
Yes, sir.
This is 7 volt. Here there is a resistor. In this loop there is no resistor, no.
In that loop only there is resistor, sir.
Here also.
Yes, there is resistor, sir. And there is a Vin which is greater than 9 volts, sir.
Where is Vin?
It is parallel to 7 volts, sir. There is a resistor.
Here also there is a resistor.
No, sir. Above the Vin there is a resistor.
Here.
Yes, sir. That is Vin is greater than 9 volts, sir. So I want to know the voltage across the resistor which is above 3 volts.
See, this is already 7, no?
Yes, sir.
This is already 3. 7 minus 3, 4 will be there across this.
Okay.
Across this resistor, this is 9. 9 minus 7, 2 volt will be dropped.
Okay, sir.
Yeah.
Thank you, sir.
సార్, గుడ్ ఈవినింగ్ సార్.
Yes.
సార్, మనము ఈ దాని ఒకసారి మనం జిఎం అనుకున్నాం చూసినాం సార్, ఒక పెద్ద లాస్ట్ మెథడ్. ఎట్లా అంటే మనం పాటలు చేసి అందుట్లో మనము ఇట్లా వోల్టేజ్ గెయిన్ వేసుకొని కూడా కనుక్కోవచ్చు కదా సార్, డినామినేటర్ వేసి.
అంతే అంతే కనుక్కోవచ్చు. సింగిల్ కరెంట్
కానీ
వస్తుంది కదా.
వస్తుంది సార్. కానీ సార్ ఇక్కడ మనకి ఒకటి కామన్ కలెక్టర్ వచ్చేసి ఇన్పుట్ గా మనం ఒకటి అవతల ఎమిటర్ టర్మినల్
అవును, ఆ రెండిట్లో ఒకటే కరెంట్ పోవట్లేదుగా.
పోవట్లేదు సార్. AV/GM దానికి ఎలా కనుక్కోవాలి సార్? పైన మనకి అవుట్పుట్ లో రెసిస్టెన్స్ కూడా లేదు కదా సార్ కలెక్టర్ దగ్గర.
అదేనన్నా నేను అనేది. డార్లింగ్టన్ పేరా నువ్వు అనేది?
డార్లింగ్టన్ పేరు కాదు సార్, మనకి కామన్ గా డార్లింగ్టన్ పేరే సార్. మనకి GM కనుక్కున్నాం కదా సార్ ఒకటి ఇట్లా.
అదే నేను అనేది ఏంటంటే ఇప్పుడు అందులో ఇందులో ఒకటే కరెంట్ ఉంటే ఒకటే రాస్తాము. కానీ ఇప్పుడు ఇక్కడ ఒక కరెంటు అక్కడ వేరే కరెంట్ ఉన్నాయి కదా, 2 స్టేజ్ అయిపోద్ది అంటున్నా. 2 స్టేజ్ యాంప్లిఫైర్ ఉన్నప్పుడు ముక్కలు చేయాలి కదా.
ఎస్ సార్, కానీ ముక్కలు చేసినా మనకి లాస్ట్ దానికి వోల్టేజ్ గెయిన్ రాయిపోతుంది సార్. నాకు అది GM ఎలా కనుక్కోవాలో
ఒకసారి వాట్సాప్ లో పంపి, నేను చెప్తా
సార్. వాట్సాప్ లో ఆల్రెడీ సెండ్ చేసిన సార్.
ఇదే కదా నువ్వు చెప్పింది?
నో సార్, ఈ రివర్స్ లో సార్ మనకి ఎమిటర్ టర్మినల్ ఇచ్చింది కింద ఇన్పుట్
ఇలా ఇచ్చాడు కదా
ఎమిటర్ టర్మినల్. ఎస్ సార్,
ఇది 1/GM సేమ్ కరెంటే కదా.
మనకి 0.5 GM వచ్చింది సార్ అక్కడ. GM టోటల్ ట్రాన్స్కరెంట్ పైన I0 వస్తుంది సెకండరీ ట్రాన్సిస్టర్ లో. ఇటు
ఇందులో I0 కదా,
ఇందులో I0 ఇక్కడ Vin.
అదే నేను చెప్పేది. 1/GM + 1/GM అంటే 0.5 GM కదా. 1 హోల్ డివైడెడ్ బై 1/GM + 1/GM.
ఎస్ సార్, దీనికి
GM/2 సరిపోయింది కదా.
ఓకే సార్, ఓకే సార్, థ్యాంక్ యూ వెరీ మచ్ సార్.
Hello, sir.
Yeah.
Good evening, sir. So, for positive feedback, do we always need to apply symmetrical method to find the output?
For positive feedback?
Positive feedback op amp. If we have to find output, what is output? GATE 2020 question, sin T was applied, and we have to find output for that, and we got symmetrical method, constant voltage of +5.
Yes, yes.
Yes, sir.
Positive
sir,
feedback means
so
you have to assume
how
output,
do we know that we have
and
to
then
apply
you have to find the input. You are right. You have to
Sir,
first find the output.
How do we know that
Either
we have to apply
plus
symmetrical?
VSAT or minus VSAT, and then backtrack and find the input.
Okay, sir. Thank you, sir.
Yeah.
Sir, hello, sir.
Yeah.
Sir, in Zener breakdown, it's short circuit or open circuit, sir?
Zener is breakdown. You have to replace it by a voltage source.
Yes, sir.
Constant voltage source you have to replace.
VOC.
Breakdown voltage. If Zener is forward bias, constant DC voltage of 0.7 volts.
Yes, sir.
0.7 volts for forward, VZ for reverse.
Reverse. Okay, sir.
Anybody else?
Hello, sir.
Yeah, we'll stop.
Hello.
Yes.
Hello, sir.
Yes, tell me.
Sir, I have a doubt, sir. Can you explain what is unity gain frequency? I have a doubt, sir.
It is a frequency where the gain is 1.
Gain is that is closed loop gain.
Yeah.
If it is open loop, then we can say unity gain frequency.
Yeah. Open loop gain, unity gain frequency, and closed loop gain, unity gain frequency are same. That is called the gain bandwidth product. The gain bandwidth product will not change for open loop or closed loop.
And it is valid for positive feedback also.
No. There is no question of positive feedback. There is no question of frequency. Output will be only plus VSAT or minus VSAT. What frequency you will calculate if an op amp is saturated?
Yes. If it is not saturated, sir,
then it is negative feedback, no?
Oh, okay, sir. Okay, sir. And I have a problem, sir, of previous classes, or I think long back, sir, about one circuit. Can I ask here, sir?
Tell me. Yeah, you can send me on WhatsApp, no? You have any doubt?
I have a small doubt, sir.
Yeah.
Sir, you have drawn one phase compensation filter, I think, long back, sir, in all pass filter circuit in op-amp only.
Okay.
There, sir, you have said that it can compensate. That in capacity.
0 to minus 180. Yeah.
0 to minus 180, sir. Sir, I want circuit of if it can compensate, sir, 0 to 180 degree between.
Then you have to interchange the resistor and capacitor. That problem I have already given in the material, volume 2.
Okay, sir.
I have
Which
given
resistor?
2 all-pass filters in volume 2. One
Yes,
for
sir.
compensating for any signal between 0 to minus 180.
Yes,
The
sir.
other one compensates for 0 to plus 180.
Okay, so sir, which resistance capacity, that is feedback R and that C, that is
Not
connected to
feedback. The R and C we have to interchange. If I have the book, I can show you now.
I have a doubt, sir. That is which RNC we have to interchange, sir.
No, but there are only 2 questions on all-pass filter, no? In volume 2. Do you have volume 2 with you?
Right now, no, sir, but I can see later, sir.
Yeah. You have volume 2, or at least ask your friend to give you a snap. I
Okay,
will
sir.
show you. Otherwise, I will take a snap and send you on WhatsApp.
Okay, sir. Okay.
Yeah.
Sir, can you tell which resistor? Because there are 2 resistors at the input at inverting terminal, non-inverting terminal.
No, that RC, those 2 resistors you should not disturb. Feedback wala.
That
The input RC you have to interchange, I believe.
input RC. Okay, that inverting terminal to output voltage, that resistor and capacitor.
Simple. R and C if you interchange.
Yes, sir.
Then maybe you can get a phase shift, because feedback resistor and input R you should not change. R same. This RC in the non-inverting terminal you have to change.
RC non-inverting. That means capacitor first connected and
Yeah. Try that. First capacitor, then resistor. See the transfer function.
Okay, sir. First resistor, that in VP side, that in first resistor and
simple.
then
See, SCR minus 1 by SCR plus 1 we have got now.
Yes, sir.
1 minus SCR by 1 plus SCR you bring here.
Okay, sir. Okay, sir. Okay, sir. I will do it, sir.
Yeah.
Otherwise, I will ask in WhatsApp, sir.
Yeah.
Okay, sir. Okay, sir. Okay, thank you, sir.
Okay, thank you then. I'll wind up.